Look up at the night sky. You see a sea of tranquil, twinkling lights, a familiar picture of cosmic order and predictable beauty. It's a view that suggests a universe governed by neat, understandable rules. But what if that sense of order is an illusion? What if everything we think we know about the cosmos, all the laws of physics we've painstakingly written in our textbooks, are merely suggestions to the universe, and that space itself is filled with phenomena that gleefully break them? This isn't science fiction. This is the startling reality that modern astronomy continues to uncover, a reality where the universe operates on a logic so alien, it defies our very definition of the possible. We are about to embark on a journey to the very edge of understanding, to explore 30 breathtaking instances where the cosmos looked at our scientific laws and simply chose to ignore them. This journey is more than a simple list of oddities. It is a voyage into the heart of a profound mystery. Each of these 30 anomalies is a crack in the foundation of our knowledge, a glimpse into a deeper, more complex reality that lies just beyond our current grasp. We will encounter stars that are older than the universe itself, galaxies that spin in ways that should tear them apart, and particles traveling faster than the speed of light. We will confront the chilling emptiness of the Boötes void and the impossible brightness of quasars, each one a cosmic rebellion against our expectations. These aren't just errors in our data, they are the universe's way of challenging us, of pushing the human intellect to expand, to question, and to dream bigger. So prepare to have your perception of reality stretched and reshaped. The story we are about to tell is one of supreme cosmic defiance, a collection of the universe's greatest puzzles that continue to baffle the brightest minds on our planet. It is a testament to the fact that the greatest adventures are not just about finding answers, but about discovering better, more profound questions. As we count down these 30 times space has defied scientific laws, remember that you are not just a spectator. You are a participant in this grand, ongoing investigation, joining a lineage of curious minds who have always looked to the stars and dared to ask, what if we're wrong? The answers, as you will soon see, are more astonishing than anything we could have possibly imagined. Let's begin our voyage with a mystery that held scientists in suspense for over 3 decades, a puzzle that started not with a bang but with a barely perceptible drift. In the early 1970s, humanity was taking its first deliberate steps beyond the inner solar system. The Pioneer 10 and Pioneer 11 spacecraft, our pioneering envoys to the outer planets, were on their way to make history. Yet, as they journeyed farther from the sun than any human-made object had before, something peculiar happened. A tiny, unaccounted-for force began to tug on them, an almost imperceptible brake applied from an unknown source. This was the Pioneer anomaly, a deviation so small it could be compared to the gravitational pull of a single grain of sand, yet its implications were cosmic in scale. For years, this persistent deceleration defied every conventional explanation, whispering the tantalizing possibility that our most fundamental understanding of gravity might be incomplete. Imagine the scene in Mission Control. Teams of brilliant engineers and astrophysicists, equipped with the most advanced technology of the age, were meticulously tracking the spacecraft's paths. They accounted for every known force, the gravity of every planet, the sun, even the larger asteroids, the subtle push of the solar wind, the minuscule drag of interplanetary dust. Their mathematical models were masterpieces of precision. Yet the pioneers were falling behind schedule, not by much, just a few thousand kilometers each year, a discrepancy equivalent to the width of the United States over an entire decade. But in the unforgiving realm of orbital mechanics, where calculations are measured in fractions of a second, this was a glaring error. It was as if the universe itself was adding an extra, unseen rule to the game of gravity, and for a long time we couldn't find it in the rulebook. The implication sent shockwaves through the world of theoretical physics. Could this be evidence of a fifth fundamental force? Was it a hint that Einstein's theory of general relativity needed a modification at the vast scales of the solar system? Some proposed exotic forms of dark matter exerting a drag in the outer solar system. Others speculated about a potential error in our understanding of the gravitational constant itself. The Pioneer anomaly became a beacon for those searching for the next revolution in physics, a tiny crack through which a new theory of everything might eventually flood in. It was a classic, thrilling scientific detective story with the entire cosmos as the crime scene. The resolution, when it finally came, was a masterclass in scientific humility and painstaking investigation. It turned out the culprit wasn't a new law of physics, but something far more mundane, yet fiendishly difficult to detect. The answer was heat. Not the heat from the sun, but the tiny, waste heat radiating from the spacecraft's own nuclear power generators and electronic systems. This thermal radiation wasn't radiating away perfectly evenly in all directions. A little more heat was being emitted from the back of the spacecraft's dish-shaped antenna, which was always pointed back towards Earth. This created a tiny but constant recoil force, a photon push, much like the gentle thrust from a very, very weak photon rocket. This anisotropic or directionally uneven thermal radiation was just enough to produce the exact anomalous deceleration that had perplexed scientists for so long. The case was ultimately closed not by a grand new theory, but by incredibly detailed computer models and the recovery of decades-old engineering data, confirming that the spacecraft itself had been gently breaking its own journey all along. What makes the Pioneer anomaly so profound, even after its resolution, is the lesson it teaches us about the scientific process. It stands as a powerful reminder that our search for new physics must always begin with a rigorous search for mundane explanations. It demonstrates the incredible precision of our modern measurements, capable of detecting an effect so minuscule, and it highlights a beautiful truth. Sometimes the universe isn't breaking the rules we wrote, it's simply following them in a way we hadn't yet learned to see. This first mystery sets the stage perfectly for our countdown, because it shows that even when an anomaly is solved, the journey of questioning and discovery it sparks is a victory for science in itself. But if the Pioneer anomaly taught us that the answer can sometimes be hiding in our own technology, our next mystery serves as a stark reminder that some cosmic puzzles are far from solved. This one occurs much closer to home, in the gravitational whirlpool surrounding our own planet. For decades, mission controllers have been using a well-understood cosmic slingshot technique, a gravity assist or planetary flyby. The concept is elegant and relies on the unwavering laws of orbital mechanics. A spacecraft steals a tiny bit of a planet's orbital momentum as it swings by, using that energy to accelerate on its way to distant targets. The math for these maneuvers is precise, honed over countless missions, but on several dramatic occasions that math has broken down and our spacecraft have experienced strange, unexpected jumps in speed. This is the flyby anomaly, and it suggests that something very peculiar is happening in Earth's own backyard. The story truly captured attention with the Galileo spacecraft in December 1990. As it swung by Earth to gain momentum for its long journey to Jupiter, something was off. The spacecraft emerged from its fly by moving ever so slightly faster than the most detailed calculations had predicted. The difference was tiny, a matter of just a few millimeters per second, but it was there and it was undeniable. This wasn't a one-time glitch. A few years later, the near-Shoemaker spacecraft on its way to study an asteroid performed a similar Earth flyby and once again experienced an unaccounted-for speed boost. Other missions, like the Rosetta Comet Chaser, also showed smaller but still baffling deviations. The pattern was clear. During these critical gravitational maneuvers, our spacecraft were playing by a slightly different set of rules. The immediate search for an explanation sent scientists scrambling. Could it be something as straightforward as an error in modeling Earth's atmosphere? Perhaps the tenuous outer fringes of our air were exerting a tiny, uncalculated drag or an unexpected push. Others looked to Earth's rotation, suggesting that the planet's spin might be imparting a subtle, frame-dragging effect on the passing spacecraft, a phenomenon predicted by general relativity but thought to be far too weak to cause this kind of anomaly. But as each of these conventional ideas was tested against the data, they fell short. The precision of the anomaly, its apparent dependence on the spacecraft's incoming and outgoing trajectory, pointed to something more fundamental. This led to much more exotic proposals. What if a halo of dark matter was gravitationally bound to Earth? Could this invisible, mysterious substance be tweaking the orbits of our spacecraft in ways our equations couldn't see? Or, even more radically, were we witnessing a tiny flaw in Einstein's theory of general relativity itself, a chink in the armor of our most robust theory of gravity that only becomes apparent during these very specific high-velocity celestial dances? The enduring enigma of the flyby anomaly is what makes it so compelling. Unlike the Pioneer puzzle, this one refuses to be neatly solved. No single explanation, from the mundane to the revolutionary, has managed to account for all the observed data across every flyby. It remains an open case in the logs of space agencies around the world. This persistent mystery forces a humbling admission. Even in the space immediately around our home world, a region we have mapped and measured with incredible detail, there may still be fundamental physics at work that we do not yet comprehend. It's a ghost in the machine of orbital mechanics, a whisper from the universe that our grasp on the rules, even here at home, might be slightly more tenuous than we believed. From the fleeting ghosts in our own orbital backyard, we now turn to a phantom of truly cosmic proportions, a substance so pervasive that it forms the very skeleton of the universe, yet remains completely invisible to our most powerful telescopes. This is the mystery of dark matter, and its story begins not with a flash of light, but with the careful, meticulous observation of how entire galaxies move. The clues first emerged almost a century ago with a brilliant and often cantankerous astronomer named Fritz Zwicky. While studying the Coma cluster, a vast collection of over 1,000 galaxies millions of light-years away, Zwicky noticed something profoundly unsettling. The individual galaxies within the cluster were whizzing around at tremendous speeds, so fast that the combined gravitational pull of all the stars, gas, and dust he could see should have been utterly incapable of holding the cluster together. According to the well-established laws of gravity, the Coma cluster should have flown apart eons ago. Zwicky concluded that there must be some form of unseen matter, which he called dunkel materie, or dark matter, providing the extra gravitational glue to keep everything bound. For decades, Zwicky's bold proposal was largely dismissed or ignored by the astronomical community. It would take another 40 years and the painstaking work of a pioneering astronomer named Vera Rubin to bring the dark matter puzzle to the forefront of physics. Rubin was studying the rotation of spiral galaxies. According to Newtonian physics, stars orbiting the center of a galaxy should behave much like planets orbiting the Sun. Those closer to the center, where most of the visible mass is concentrated, should orbit very quickly. Stars farther out in the galactic suburbs, where the disk thins out, should move much more slowly. But what Rubin and her colleague Cant found was completely different. They discovered that stars at the very edge of galaxies were orbiting just as fast as those near the center. The entire galactic rotation curve was flat. This was a direct and stunning violation of gravitational expectations. The only plausible explanation was that these galaxies were embedded within vast, massive halos of some invisible material halos that extended far beyond the visible edge of the galaxy, providing the extra gravitational pull to keep the outer stars whipping around at such incredible speeds. Think of a galaxy not as a simple disk of stars, but as a tiny, glittering city lit by streetlights, embedded in the center of an immense, invisible mountain made of fog. We can only see the city lights, but it's the gravitational pull of the entire massive, dark mountain that dictates how fast everything moves on its outskirts. This is the essence of the dark matter paradigm. The implications are staggering. The laws of physics, as written by Newton and refined by Einstein, are not wrong per se. They are simply incomplete when applied to the largest scales. The universe is obeying the rules of gravity, but it's using a form of matter we cannot see to do it. This invisible substance does not emit, absorb, or reflect any form of light. It interacts with the ordinary matter that makes up our world, you, me, and every star we see, only through the force of gravity. It is a ghost that we can only detect by watching how it pushes the visible actors around the cosmic stage. The evidence for this cosmic phantom has only mounted over the years, creating a consensus that dark matter makes up roughly 27% of the entire mass energy content of the universe. Ordinary matter, everything from atoms to black holes, comprises a mere 5%. We see its gravitational fingerprint everywhere. The way massive galaxy clusters bend the light from more distant objects, an effect known as gravitational lensing, reveals far more mass than is visible. The precise patterns of the cosmic microwave background radiation, the afterglow of the Big Bang, can only be explained if dark matter was present in the early universe to help clump matter together and form the first galaxies. Every line of inquiry points to the same inescapable conclusion. The cosmos we see is just the tip of a vast, hidden iceberg. For decades, the leading theoretical candidate for dark matter has been a hypothetical particle known as a WIMP, a weakly interacting massive particle. These particles would be heavy and slow-moving, and vast experiments deep underground have been built to try and catch one as it passes effortlessly through the Earth. Yet, despite decades of searching, not a single definitive WIMP has been detected. This persistent non-detection has led to a fascinating crossroads in physics. Are our experiments just not sensitive enough, or is dark matter something even more exotic and strange? Some theorists propose it could be primordial black holes formed in the first moments after the Big Bang. Others suggest we need to modify the laws of gravity themselves, with theories like MUND, modified Newtonian dynamics, which attempt to explain the galactic rotation curves without any invisible matter. But MUND and its variants have struggled to explain all the evidence, particularly the observations from colliding galaxy clusters where the gravitational effects and the visible matter are clearly separated. The mystery of dark matter, therefore, remains one of the greatest and most humbling defiances of our scientific expectations. It is a clear signal that our census of the universe is profoundly incomplete, and that the most dominant component of the cosmic landscape is a complete and utter enigma. If the ghostly pull of dark matter represents a cosmic tug of war we didn't know we were fighting, then our next discovery revealed an opponent of unimaginable power operating on the very fabric of spacetime itself. This is the story of dark energy, a finding so shocking and counterintuitive that it completely upended our vision of the universe's ultimate fate. For most of the 20th century, astronomers were locked in a fundamental debate. Did the universe have enough matter for gravity to eventually halt its expansion, leading to a big crunch, or would it simply coast forever, slowly thinning out into a cold, dark eternity? The prevailing wisdom, backed by Einstein's own equations, favored a cosmic slowdown. Gravity, after all, is an attractive force. Throw a ball into the air and it slows down as Earth's gravity pulls it back. It seemed only logical that the universe, born in a colossal explosion, would exhibit the same behavior, with the collective gravity of all its galaxies acting as a cosmic brake. But in 1998, two independent teams of researchers made an observation that shattered this assumption, revealing a reality far stranger than anyone had dared to imagine. These teams were using the world's most powerful telescopes to study a specific kind of stellar explosion, Type 1, a supernova. Think of these events as the universe's ultimate standard candles. At Type 1, a supernova occurs when a white dwarf star steals just enough material from a companion to cross a critical mass threshold, triggering a thermonuclear explosion of such predictable brightness that astronomers can use it to measure vast cosmic distances with incredible precision. By observing how much dimmer these supernovae appeared in extremely distant galaxies, the teams could calculate exactly how much the universe had expanded since the moment the star exploded billions of years ago. They were fully expecting to confirm the universe was expanding, but at an ever-slowing rate. What they found instead was breathtaking. The most distant supernovae were significantly fainter than their models predicted. This could only mean one thing: those ancient galaxies were much farther away than anyone had thought. The expansion of the universe wasn't slowing down, it was speeding up. It was as if that ball we threw in the air, instead of slowing and falling back, suddenly kicked on a rocket and shot away into the sky at an ever-increasing velocity. The implications of this discovery were nothing short of revolutionary. Something was actively working against gravity, a pervasive force that was stretching the very space-time between galaxies at an accelerating rate. This mysterious something was dubbed dark energy. To understand its profound weirdness, consider the nature of gravity as a force that pulls things together, drawing matter into clusters, galaxies, and stars. Dark energy does the exact opposite. It is a cosmic repulsion, a kind of anti-gravity that pushes the universe apart. The most unsettling part is its sheer dominance. When we tally up the entire contents of the cosmos, the result is almost unbelievable. All the stars, planets, nebulae, and every single atom that makes up you and me, all the ordinary matter accounts for a paltry 5% of the universe. Dark matter, that invisible gravitational scaffold, makes up a much larger 27%, but dark energy, it constitutes a staggering 68% of the entire cosmos. We live in a universe where the dominant component, the primary driver of cosmic evolution, is a force that causes emptiness itself to expand. The leading theoretical explanation for dark energy comes from a concept Einstein himself proposed and then later called his greatest blunder. He introduced a cosmological constant into his equations of general relativity, a term representing a constant energy density filling space uniformly. This inherent energy of the vacuum would indeed produce a repulsive gravitational effect, perfectly matching the observed acceleration. The problem is that when quantum physicists try to calculate the expected value of this vacuum energy from first principles, their theoretical predictions are off by a factor of 10 to the power of 120. This is arguably the worst prediction in the entire history of physics. A number so incomprehensibly large that it highlights a fundamental disconnect between our understanding of the cosmos on the largest scales and the rules governing the quantum world on the smallest. If the cosmological constant is the answer, we have no idea why it has the incredibly tiny, yet precisely tuned, value that it does. Other theories suggest dark energy might not be constant at all, but a dynamic field that has changed over the life of the universe, an idea sometimes called quintessence. Yet with our current data, it remains indistinguishable from a simple cosmological constant, a steady, relentless pressure that is now permanently woven into the fate of everything. This discovery paints a chilling and lonely portrait of our cosmic future. In a dark energy-dominated universe, the acceleration will continue unabated. Billions of years from now, galaxies outside our own local group will be pushed away by the expanding space-time until they are moving away from us faster than the speed of light. Their light will no longer be able to reach us, and they will vanish from our sky forever. The universe for any future astronomers in our galaxy will be an island of stars in an infinite, black and empty void, with no evidence that other galaxies ever existed. The fate of the cosmos appears to be not a fiery collapse or a gentle coast, but a perpetual, accelerating drift into ultimate isolation and cold. The mystery of dark energy, therefore, is more than just a puzzle about a strange force. It is a question about the ultimate destiny of all existence, a dramatic and ongoing defiance of our most basic expectations for how gravity should shape the cosmos we call home. If the relentless push of dark energy describes the grandest canvas of our expanding universe, then the very motion of our own cosmic home tells a different, more intimate story of a mysterious, irresistible pull. For decades, astronomers have known that our Milky Way galaxy is not simply drifting aimlessly through the void. It is on a collision course with its giant neighbor, the Andromeda Galaxy, an event set to occur billions of years from now. But this local dance is just one small part of a much larger and far more peculiar journey. Our entire local group of galaxies, along with thousands of others, is being swept sideways at an astonishing velocity of over 1 million miles per hour toward a specific, seemingly empty point in the depths of space. This is the mystery of the Great Attractor, a colossal gravitational anomaly that for years represented one of the most profound and confounding puzzles in all of cosmology. The story of its discovery began with careful maps of the cosmic microwave background, the faint afterglow of the Big Bang. This radiation creates a fundamental reference frame for the universe, a backdrop against which we can measure our own local motion. When scientists measured this, they found our solar system was moving relative to this background. This wasn't entirely unexpected, as the gravity of familiar objects like the Virgo cluster, the largest nearby collection of galaxies, was known to be tugging on us. But as the data became more precise, a startling truth emerged. Even after accounting for the pull of Virgo and every other known nearby structure, a huge component of our motion remained unaccounted for. A vast, unseen concentration of mass, located in the general direction of the southern constellations Centaurus and Hydra, was reeling us in. This unknown gravitational source was dubbed the Great Attractor, and its apparent power was staggering, influencing the motion of an entire swath of the local universe. For a long time, studying this cosmic behemoth was like trying to identify a distant mountain peak while standing in a dense, foggy forest. The Great Attractor lies almost perfectly behind the plane of our own Milky Way, in a region astronomers call the zone of avoidance. This is not a place of cosmic danger, but one of observational frustration. It's the thick, dusty, and star-choked central disk of our galaxy. Just as fog and city lights obscure our view of the stars from Earth, this galactic plane blocks almost all visible light from the universe beyond. For traditional optical telescopes, the Great Attractor was hidden behind a nearly impenetrable wall of cosmic clutter, leaving its true nature a matter of pure speculation. Was it a single, unimaginably massive object, a colossal black hole of impossible scale, or something else entirely, a structure that defied all classification? The turning point came with the advent of new technologies that could see through the galactic fog. Telescopes that observe the sky in radio waves and X-rays, wavelengths that can penetrate the obscuring dust, began to paint a new picture. What they revealed was not a single monolithic attractor, but something arguably even more grand, an immense supercluster of galaxies. This structure, now known as the Laniakea supercluster, of which our own Milky Way is a mere outlying suburb, redefined our cosmic address. The Great Attractor is not a lone entity, but the gravitational center of this vast continent of galaxies, a dense knot where the Norma cluster and other massive galaxy clusters are concentrated. Its pull is the combined gravity of hundreds of thousands of galaxies all clumped together in one region of space, a density so immense that it dictates the flow of galaxies for hundreds of millions of light years around it. Yet, even with this revelation, the mystery has not been entirely solved. The sheer number of galaxies in the Laniakea region, while massive, still does not seem to fully account for the observed velocity of our motion. There is a lingering discrepancy, a suggestion that the great attractor itself might be feeling a pull from something even larger and more distant. This points to an even more immense structure lurking in the shadows, often referred to as the Shapley attractor, a supercluster hundreds of millions of light years away that may be the ultimate source of the gravitational tide influencing our entire galactic neighborhood. This creates a cosmic hierarchy of pulls and tugs, a Russian nesting doll of gravitational influences that stretches across the observable universe. The enduring lesson of the Great Attractor is one of scale and humility. It reminds us that our view of the cosmos has been historically myopic, and that the true architecture of the universe, built on the invisible scaffolding of dark matter, is a web of such immense proportions that we are only just beginning to trace its outlines. But just as we begin to map these grand, flowing rivers of galaxies, a discovery from the earliest light of the universe throws a wrench into our most fundamental assumption about the cosmos itself. This is the mystery of the axis of evil, a finding so statistically bizarre and philosophically unsettling that its very name reflects the profound challenge it poses to cosmology. To understand why this anomaly is so shocking, we first need to grasp a cornerstone of modern science, the cosmological principle. This principle states that, on the largest scales, the universe is both homogeneous and isotropic. Homogeneous means the cosmos is roughly the same everywhere, no single location is special. Isotropic means it looks the same in every direction you look, there are no preferred axes or directions. This idea that we do not occupy a privileged place in the universe is the very foundation upon which virtually all of modern cosmology is built. It's what allows us to apply the same physical laws everywhere and to believe that observations from our tiny planet can tell us about the cosmos as a whole. Our best and most precise snapshot of this early, homogeneous universe is the cosmic microwave background, the CMB. This is the faint, remnant heat from the Big Bang, a bath of microwave radiation that fills all of space, emitted when the universe was just 380,000 years old. It is the oldest light we can see. For decades, satellites like COBE, WMAP, and most recently Planck have mapped this radiation with incredible precision, revealing a nearly uniform temperature of just 2.7 degrees above absolute zero. The key to understanding the universe's structure lies in the tiny, minuscule fluctuations in this temperature variations of only 1 part in 100,000. These tiny hot and cold spots are the seeds of all future structure, the gravitational wells that would eventually collapse to form galaxies, clusters, and superclusters. According to the cosmological principle, these fluctuations should be completely random, like a static pattern on an old television, with no correlation to our local position billions of years later. They should show no preferred alignment or direction whatsoever. This is where the axis of evil appears, and it's not a single anomaly, but a collection of several strange correlations that all seem to point in the same disturbing direction. When scientists analyzed the full sky maps from the Planck satellite, they found that the larger scale fluctuations in the CMB are not entirely random. Instead, they appear to have a subtle alignment or a preferred plane that seems to correlate with the ecliptic plane of our own solar system. Furthermore, the quadrupole and octupole moments, which are specific mathematical ways of describing the larger, warmer and cooler patches on the map, are not oriented randomly as expected. They are aligned with each other, and their axis points suspiciously close to the direction of the sun's motion through the galaxy. The probability of such an alignment happening by pure chance is astronomically low, something like 1 in many thousands. It's as if you drew a map of the entire Earth's geology and found that all the major mountain ranges were subtly aligned with the street you live on. The implication is staggering. The oldest light in the universe seems to know about our local cosmic neighborhood, a connection that should be utterly impossible. The immediate and most obvious suspicion was some kind of systematic error or contamination from within our own solar system. Perhaps the spacecraft itself was picking up interference from the solar wind or dust within our planetary system that was imitating a cosmological signal. Teams of researchers have spent years exhaustively searching for such a local contaminant. Others considered the possibility of galactic foregrounds, that light from our own Milky Way galaxy, which must be carefully subtracted from the CMB data, was not being removed perfectly, leaving behind a residual pattern that just happens to align with the solar system. Yet, after all this painstaking work, the anomaly persists. It's still there in the cleaned, foreground subtracted data. This stubborn refusal to be explained away is what makes the axis of evil so compelling and so troubling for cosmologists. If the effect is real and cosmological in origin, the implications are profound and force us to consider two equally radical possibilities. The first is that the cosmological principle is wrong, and we do, in fact, live in a special place in the universe. This would be a monumental overturning of a foundational pillar of science, hearkening back to a pre-Copernican idea that humanity occupies a central or privileged location. The second, and perhaps more palatable, possibility is that our understanding of the very early universe is incomplete. The standard model of cosmology relies on a period of rapid expansion called inflation, which is thought to have stretched a microscopic patch of space into our entire observable universe, ensuring its homogeneity. The axis of evil could be a hint that this inflationary epoch was more complex than we think, perhaps involving multiple fields or leaving behind a fossil directionality imprinted on the cosmos. It might even point to the universe having a topologically complex shape on scales larger than we can observe, like a crystal with a preferred structure. The mystery of the axis of evil, therefore, is not just about a strange alignment in a map. It is a direct challenge to the randomness and simplicity of our cosmic origins, a whisper from the dawn of time that the universe might be far more peculiar and far more interconnected than our most cherished principles have led us to believe. Moving from the vast, directional puzzles of the cosmos, we descend into the microscopic realm of the universe's first moments, where a different kind of defiance is etched into the very elements that compose us. This is the lithium problem, a crisis that unfolds not over billions of light years, but within the first 20 minutes of existence itself. Our most successful and precise theory for the origin of the lightest elements in the cosmos is Big Bang nucleosynthesis. This elegant model describes how, in that seething, dense furnace of the newborn universe, protons and neutrons fused together to form the first atomic nuclei. The predictions for the abundances of hydrogen, deuterium, and helium align with astronomical observations so beautifully that it stands as one of the three great pillars of evidence for the Big Bang. Yet for one specific element, the math spectacularly breaks down. The universe, it seems, produced about 3 times less lithium-7 than our textbooks insist it should have. To appreciate the depth of this problem, we need to step into that primordial cauldron. For a brief window between about 1 second and 20 minutes after the Big Bang, the entire universe had the temperature and density of the core of a star. It was a single, universe-spanning fusion reactor. During this fleeting epoch, protons and neutrons collided and stuck, forming deuterium. These deuterium nuclei then rapidly fused into helium-4, which is incredibly stable. This process gobbled up most of the available neutrons, but trace amounts of other, heavier elements were also forged in this cosmic fire. According to the meticulous calculations of nuclear physics, a specific chain of reactions should have produced a predictable amount of the next element in line, lithium-7. The models are not vague, they give a precise number. When we look out at the oldest stars in the halo of our galaxy, stars that formed from nearly pristine gas shortly after the Big Bang, we are essentially doing archaeology on the composition of the early universe. These ancient stellar fossils should preserve that original lithium abundance like a time capsule. but when we measure it, the amount of lithium-7 we see is consistently and bafflingly only 1/3 of what was predicted. The immediate question, of course, is whether our observations are simply wrong. Could these ancient stars have been somehow destroying or diluting their lithium over the billions of years since their birth? Astronomers have chased this possibility with immense care. They focus on the most pristine stars, ones with extremely low metallicities, meaning they contain very few elements heavier than lithium, confirming they are truly ancient. The surface temperatures of these stars are also just righter, around 6,000 Kelvin, similar to our Sun, a range where their atmospheres are stable enough that lithium would not sink deep into the star or be blown away by stellar winds. In this comfortable zone, the lithium abundance should be a reliable record, yet star after star tells the same story. The lithium count is far too low. It's as if we had a perfect fossil record of early life, but a key species predicted by evolutionary theory was consistently missing from every dig site. This glaring discrepancy has forced physicists to consider much more radical solutions. One compelling line of inquiry points the finger at the very laws of particle physics themselves. What if an unknown type of particle was present in those first few minutes, subtly altering the nuclear reactions? A leading candidate is a type of hypothetical particle known as an action, which was originally proposed to solve a separate, deep problem in quantum physics. These actions could have decayed into photons in the early universe, injecting extra energy and effectively lowering the temperature at a critical moment in the nucleosynthesis process. A slightly cooler bath of particles would have changed the delicate balance of fusion rates, potentially suppressing the production of lithium-7 without messing up the perfect agreement we see for deuterium and helium. Another exotic idea involves the possible decay of a speculative particle like the gravitino, the superpartner of the graviton in supersymmetry theories. Its decay could have similarly reshuffled the nuclear deck in the primordial universe. These are not wild guesses. They are serious attempts to use the lithium problem as a telescope to see beyond the standard model of particle physics, using the first 3 minutes of the universe as our laboratory. On the other hand, astrophysicists have proposed solutions that keep the particle physics intact but revolutionize our understanding of stars. Perhaps these ancient stellar fossils are not the pristine time capsules we believe them to be. What if the surfaces of these old stars are not representative of their interiors? Some models suggest that these stars could have vast, unseen interior zones where circulation currents slowly transport material from the surface down into the blazing hot core, where lithium is quickly destroyed by nuclear fusion. This process would systematically deplete the surface lithium we can observe, creating the illusion of a primordial deficit. Other, even more dramatic, proposals involve the star's environment. Could these ancient stars have formed planetary systems? If so, the accretion of rocky, lithium-poor planetary material onto the star's surface early in its life could have diluted the original abundance. While these stellar scenarios are clever, they often struggle to explain the remarkable uniformity of the lithium measurement across so many different ancient stars scattered throughout the galactic halo. The problem's persistence suggests the truth may be more fundamental, a tiny crack in the magnificent edifice of the Big Bang theory that hints at entirely new physics operating at the dawn of time. Yet another inventory of the cosmos reveals a startling shortfall, but this time it's not some exotic, invisible substance like dark matter. This time it's the very ordinary stuff that makes up you, me, every planet and every star. We are talking about baryonic matter, the protons and neutrons that form the bedrock of the atomic world. The problem is simple and profound. When we count all the baryons that should exist based on the pristine conditions of the early universe, and then we count all the baryons we can actually see in the present-day cosmos, more than half of them are gone. This is the mystery of the missing baryons, a cosmic accounting error of epic proportions where the universe seems to have misplaced the majority of its normal matter. The evidence for this discrepancy comes from two very precise and independent cosmic bookkeeping methods. The first ledger is written in the light of the cosmic microwave background. The subtle patterns in this ancient afterglow allow cosmologists to calculate the total density of baryons that existed when the universe was only 380,000 years old. It gives us a firm initial balance. The second ledger is a modern-day inventory. We can add up the mass of all the stars in all the galaxies, all the cold gas in and between them, and all the hot gas within gigantic galaxy clusters. When we do this exhaustive count, we come up drastically short. Only about 40 to 50% of the baryons that were present in the early universe can be found in these visible structures today. So where did the rest go? They haven't been destroyed, matter is conserved. They must be hiding somewhere in a form that has, until very recently, eluded our detection. The prime suspect in this cosmic whodunit is a vast, diffuse web of incredibly hot gas spread throughout the spaces between galaxies. This theoretical structure is known as the warm-hot intergalactic medium, or WIM. Picture the large-scale structure of the universe not as a collection of isolated islands, but as an immense cosmic metropolis. The galaxies and clusters are the bright, dense cities and towns. The WIM is the sprawling, barely populated suburbia and the long, tenuous highways connecting them all. This isn't a cloud of cold, easy-to-see gas. The WIM is a searing plasma, heated to temperatures between 100,000 and 10 million degrees Kelvin by the immense gravitational shocks that occurred as matter collapsed into the filaments of the cosmic web over billions of years. Gas this hot doesn't emit much visible light. Instead, it glows faintly in low-energy X-rays or absorbs light in the far ultraviolet, making it incredibly difficult to observe directly. This is where the detective work becomes a true feat of modern astronomical ingenuity. Since we can't easily see the WIM itself, we have to catch it in the act of casting a shadow. The primary technique involves using brilliant, distant light sources known as quasars. Think of a quasar as a cosmic lighthouse, a beacon powered by a supermassive black hole at the center of a galaxy, shining brightly across billions of light years. As this light travels through the universe on its way to our telescopes, it passes through these invisible filaments of the WIM. The hot gas in these filaments absorbs specific wavelengths of the quasar's light, leaving behind a unique fingerprint, a series of tiny, telltale dips in the quasar's spectrum. The challenge is that these absorption lines are exceedingly faint and spread across a very broad range of wavelengths. It's like trying to identify the chemical composition of a distant fog by analyzing the precise pattern of colors missing from a searchlight beam after it passes through. It requires incredibly sensitive space-based observatories, like the Hubble Space Telescope for ultraviolet data and the XMM Newton and Chandra observatories for X-rays, to even have a chance of spotting these spectral signatures. For years, the WIM remained a compelling theory with only fragmentary, circumstantial evidence, but recently the case has started to break open. Astronomers have begun to successfully piece together these faint absorption signals, not just from one quasar, but by stacking data from the light of many quasars that pierce the same predicted cosmic filament. In a major breakthrough, researchers using data from the Planck satellite and other observatories reported detecting the aggregate emission of the WIM in the form of a specific type of X-ray radiation, strongly suggesting they had found a large reservoir of the missing baryons. Another team, using a different technique, claimed to have weighed an entire filament between two galaxy clusters, finding it contained far more hot gas than anyone had expected. These findings are like finally getting a blurry, first-ever photograph of a creature that was once only a legend. The missing matter, it seems, wasn't truly missing at all. It was simply hiding in plain sight, woven into the hottest and most diffuse fabric of the cosmic web. Solving the mystery of the missing baryons does more than just balance the universe's books. It profoundly deepens our understanding of cosmic evolution. It confirms a key prediction of how structure forms in the universe, that most normal matter is not locked up in stars, but is instead part of a dynamic, intergalactic ecosystem. This hot, diffuse plasma is the reservoir from which galaxies form and into which they eventually recycle material. The ongoing hunt for the whim pushes our observational technology to its absolute limits, forcing us to develop new methods and new telescopes to see the unseeable. It serves as a powerful reminder that even the ordinary matter in the universe can present us with extraordinary puzzles, and that the cosmos still holds vast, hidden territories waiting to be mapped in the faintest whispers of X-rays and ultraviolet light. Now, let's shift our focus from the grand architecture of the cosmos down to the smallest, most energetic messengers arriving from the void. Imagine a single subatomic particle, a proton or the nucleus of an atom, traveling through the emptiness of space. It is so tiny it's almost a mathematical abstraction. Yet, this particle carries with it more kinetic energy than a professionally thrown fastball. Not just a little more, but millions of times more energy than the most powerful collisions we can create in our greatest particle accelerators, like the Large Hadron Collider. These are ultra-high-energy cosmic rays, and their existence is one of the most persistent and baffling anomalies in modern astrophysics. They are cosmic bullets fired from unknown sources with a ferocity that challenges our understanding of the fundamental forces of the universe. The sheer scale of their energy is almost impossible to comprehend. Scientists measure the energy of these particles in units called electron volts. The protons circulating in the Large Hadron Collider reach energies of about 13 trillion electron volts. That's a 13 followed by 12 zeros, but the ultra-high-energy cosmic rays we detect hitting our atmosphere have been recorded with energies exceeding 100 quintillion electron volts. That's a 1 followed by 20 zeros. This single, minuscule particle carries the same kinetic energy as a brick dropped from waist height, all concentrated into a space a million times smaller. When such a particle strikes the upper atmosphere, it doesn't just quietly fizzle out. It initiates a spectacular cascade of secondary particles, an enormous shower that can spread over dozens of square kilometers by the time it reaches the ground. A phenomenon we can detect with sprawling observatories like the Pierre Auger Observatory in Argentina. The very fact that we can detect them at all is a testament to their unbelievable power. But here's where the mystery truly deepens, and where the universe seems to impose a strict speed limit, only to have it blatantly ignored. In the 1960s, physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin independently predicted a fundamental barrier for such particles traveling across the vast distances of the universe. This is known as the GZK cutoff. Their reasoning was based on a simple but profound interaction. The entire universe is filled with the cosmic microwave background radiation, the faint relic photons from the Big Bang. For a cosmic ray proton traveling at over 99.9% the speed of light, these harmless, low-energy photons are no longer just a cool background glow. Due to the extreme relativistic effects from the proton's point of view, these photons are massively blue-shifted into a barrage of high-energy gamma rays. The GZK theory states that when an ultra-high-energy proton collides with one of these CMB photons, it should undergo a specific nuclear reaction, producing a short-lived particle called a pion. This process robs the proton of a significant amount of its energy. Over distances of more than about 150 million light-years, this constant ping-pong with the cosmic background should drain these protons, effectively placing a hard ceiling on the maximum energy any cosmic ray from a distant source could possibly have when it arrives at Earth. Yet, our detectors have recorded multiple cosmic rays with energies far beyond this theoretical GZK limit. This is the heart of the defiance. It's as if the universe has a posted speed limit on an interstellar highway, and we keep finding dragsters blowing past the radar gun at twice the legal maximum. The detection of these super GZK particles presents a stark puzzle with two equally challenging possible solutions. The first possibility is that these cosmic rays are coming from relatively nearby sources within our own cosmic neighborhood, within that 150 million light-year GZK horizon. If they don't have to travel very far, they wouldn't have had time to be slowed down by the CMB. But this just replaces one mystery with another. What local astrophysical object possesses an engine powerful enough to accelerate particles to such insane energies? The second, even more mind-bending possibility is that these particles are indeed coming from incredibly distant, ultra-powerful sources billions of light-years away. If that's true, then our understanding of the particle-CMB interaction, a cornerstone of particle astrophysics, must be incomplete or somehow wrong. The hunt for the source of these cosmic extreme energy particles is one of the great detective stories in science. Candidates for these natural particle accelerators have included the most violent events in the universe: active galactic nuclei, where supermassive black holes at the centers of galaxies devour matter and spew out jets of plasma at near light speed, could potentially act as giant electromagnetic cannons. Gamma-ray bursts, the most energetic explosion since the Big Bang, are another prime suspect. Some theories have even pointed to the colossal shockwaves from merging galaxy clusters. However, when we trace the incoming direction of the highest energy cosmic rays, they rarely point conclusively to any known spectacular object. The magnetic fields that permeate interstellar and intergalactic space are notoriously messy. They bend the paths of these charged particles, scrambling their trajectories and effectively erasing their return address by the time they reach us. It's like trying to find the source of a bullet by looking at the splash pattern it made in a pond after the bullet had ricocheted off a dozen trees. This scrambling effect makes pinpointing their origins incredibly difficult, leaving us with the energy of the splash but no clear shooter. The ongoing mystery of ultra-high-energy cosmic rays forces us to confront the limits of our knowledge in both particle physics and astrophysics. Their existence is a direct challenge, a piece of experimental data that defies a clear and elegant theoretical prediction. They are proof that somewhere out in the depths of space, natural processes exist that can accelerate matter to energies we can barely conceive of, let alone replicate. Every one of these particles that slams into our atmosphere is a messenger from the most extreme environments in the cosmos, carrying with it a coded message about forces and powers that we have yet to understand. Unlocking their secret would not just solve a cosmic accounting problem, it would open a window into the ultimate particle accelerators of the universe, revealing physics operating at energies and on scales that we can only dream of witnessing here on Earth. From the high-energy violence of cosmic rays, we turn to a mystery of profound silence, a single, fleeting whisper that for one brief moment seemed to carry the promise of a cosmic hello. In the long and often quiet history of the search for extraterrestrial intelligence, one event stands apart, not for what it confirmed, but for the tantalizing possibility it represented. It was a warm summer evening on August 15, 1977. At the Big Ear Radio Telescope in Delaware, Ohio, a part of Ohio State University's long-running SETI project, the machinery was engaged in its routine, automated sweep of the sky. The system was methodical, unblinking, and patient, listening for any signal that stood out from the constant, hissing static of the cosmos. And then, for exactly 72 seconds, it heard something. It wasn't a message we could decipher, but its mathematical signature was so perfect, so statistically extraordinary, that when volunteer astronomer Jerry Amon looked over the data to print out a few days later, he was moved to circle the string of alphanumeric code and write a single, powerful word in the margin: wow. The signal itself was a thing of beauty to a scientist's eye. It was a narrowband radio signal concentrated on one specific frequency. This is crucial because natural cosmic objects, pulsars, quasars, interstellar gas typically emit radio waves across a broad spectrum of frequencies. A narrowband signal, however, is the hallmark of technology. It's what you get from a radio transmitter, a deliberate, engineered signal designed to cut through the noise. Even more compelling was the frequency it occupied, 1420 MHz. This frequency sits in a uniquely quiet band of the radio spectrum, a protected zone that is naturally shielded from background interference, a window that scientists had already identified as a potential watering hole where advanced civilizations might logically choose to broadcast. The signal also exhibited the telltale sign of a celestial origin. It grew in intensity for exactly 72 seconds as the Big Ear's fixed dish, relying on the Earth's rotation, swept its focus across that particular point in the sky, reaching a peak and then fading away with perfect symmetry. Everything about it screamed artificial and extraterrestrial. The immediate and obvious next step was to listen again. The coordinates were clear, pointing to a region in the constellation Sagittarius. Eamon and his colleagues, their hearts undoubtedly racing with a mixture of excitement and scientific skepticism, returned the Big Ear to that same spot in the sky again and again. They listened for hundreds of hours. Other radio observatories around the world were alerted and trained on the location. Yet, despite decades of repeated searches with increasingly sensitive equipment, the signal never returned. It was a cosmic one-hit wonder, a shout that echoed just once across the void and then fell into an eternal, unbroken silence. This failure to find a repeat is what makes the wow signal so deeply anomalous and defies a core tenet of the scientific method, repeatability. Any natural astronomical phenomenon, like a pulsar or a flare star, should be periodic or at least recur occasionally. A deliberate broadcast from another civilization would presumably be continuous or repeated. The fact that this powerful, seemingly intelligent signal was never heard again is the central, frustrating paradox that has kept it at the forefront of SETI lore for nearly half a century. The search for a conventional explanation has been exhaustive. Could it have been a secret military satellite transmission or a reflection of a terrestrial signal off a piece of space debris? The specific frequency of 1420 MHz is supposed to be protected, reserved exclusively for astronomical research, making a terrestrial source a serious breach of international agreement, but not an impossibility. However, the signal's perfect intensity profile, matching the telescope's beam pattern as the Earth rotated, makes a nearby, human-made source highly unlikely. A signal from a satellite or debris would have behaved very differently, appearing and disappearing abruptly, not following the smooth, predictable arc of a fixed point in the heavens. Other proposals have included a comet with its cloud of hydrogen emitting a radio signature, but the specific comets proposed were not in that part of the sky on that date in 1977. Each attempted explanation has faced significant, often fatal, objections, leaving the signal stubbornly unexplained, the enduring legacy of the wow signal is not that it proved we are not alone, but that it demonstrated how a single, unverified data point can captivate the human imagination for generations. It serves as a permanent reminder of the profound challenge of searching for intelligence in a galaxy of unimaginable scale and silence. It is the ghost in the machine of SETI, a tantalizing clue that sits at the very edge of discovery, forever teasing us with the possibility that for one brief moment we were listening to the right channel at the right time and heard a whisper from another star. Its singular nature forces us to wonder, was it a transient, incredibly powerful beacon from a civilization that flickered out eons ago, its one and only message just now reaching us? Or was it something else, a natural astrophysical phenomenon so rare and peculiar that we have simply never witnessed its like again, the silence that followed the wow signal is in many ways louder and more profound than the signal itself, a cosmic riddle that continues to defy a simple answer. Just when we thought we had catalogued every kind of stellar personality, the universe presented us with a star so bizarre that it single-handedly revived one of the most ambitious ideas in science fiction. Meet KIC 8462852, more famously known as Boyajian star or Tabby star, named after the lead scientist Tabitha Boyajian, who first brought its strangeness to the world's attention. This seemingly ordinary star, slightly larger and hotter than our own Sun, lies about 1,400 light-years away in the constellation Cygnus. It was the Kepler Space Telescope, a mission designed to find planets by spotting the tiny, periodic dimming they cause as they cross their star's face, that first spotted this celestial oddity. But what Kepler found was not the gentle, repeating dip of a planet. Instead, the data revealed a light curve that looked less like a clockwork solar system and more like a frantic heartbeat, with drops in brightness so deep and so chaotic that they defied every conventional explanation in the astronomer's playbook. The sheer depth and irregularity of the dimming events were what made this star an instant celebrity in the world of astronomy. A typical planet like Jupiter transiting a Sun-like star would cause a dip of about 1%. Even a huge planet would struggle to block more than a few percent of the star's light. Tabby's star, however, experienced dips of up to 22%. That's not a planet, that's an object or a collection of objects blocking nearly a quarter of the star's entire output. To put that in perspective, if something were to pass in front of our Sun and dim it by 22%, the object would have to be truly colossal, far larger than the star itself. Furthermore, the dips were completely aperiodic. There was no regular rhythm, no predictable pattern. Some dimmings would last for days, while others would be sharp and brief. The star would sometimes fade gradually and then snap back to full brightness with startling speed. This was not the signature of a clean, circular orbit. It was the messy, unpredictable light curve of a star in profound distress, or one that was being systematically harvested. Faced with such an unprecedented signal, astronomers did what they do best. They proposed hypotheses, starting with the most natural ones. The first and most conservative explanation was a massive, swarming cloud of comets. The idea was that a family of millions of comets, perhaps disturbed by a passing star, could have been drawn in towards Tabby's star. As they began to break up under the intense heat, they would create an enormous, irregular cloud of dust and debris, which could then cause the random, deep dimming we observed. While this was a creative solution, it had significant problems. To block 22% of the star's light, the comet swarm would have to be unimaginably vast, requiring more comets than exist in our entire solar system's Oort cloud. Furthermore, such a catastrophic event would be expected to produce a tremendous amount of infrared radiation, as the dust cloud would heat up and glow. When astronomers pointed the Spitzer Space Telescope at Tabby's star, they found a notable lack of this excess infrared heat. The comet hypothesis was straining under the weight of the evidence. It was this very lack of a satisfying natural explanation that opened the door to a far more speculative, yet irresistibly fascinating idea: alien megastructures. The concept, first proposed by physicist Freeman Dyson, imagines an advanced civilization so energy-hungry that it constructs a vast swarm of energy-collecting satellites to completely enclose its star, capturing nearly all of its luminous output. Such a structure, known as a Dyson sphere, would not be a solid shell, but a dense, rotating constellation of solar panels orbiting the star. This swarm would be irregular in shape, causing exactly the kind of chaotic, deep, and aperiodic dimming that Kepler observed. The hypothesis was not that astronomers were claiming to have found aliens, but rather that, for the first time, we had an observation so anomalous that an artificial origin had to be considered as a legitimate, if remote, possibility. This single idea catapulted Tabby's star from an obscure astronomical curiosity to a global sensation. a symbol of humanity's enduring hope that we might not be alone in a universe that seems increasingly strange. The scientific response to this mystery has been one of the most public and collaborative in modern history. When traditional grant funding for further observations ran short, Tabitha Boyajian and her colleagues turned to the public, launching a highly successful Kickstarter campaign. This allowed them to secure time on a global network of ground-based telescopes to monitor the star continuously, catching it in the act of dimming. The data that followed only added to the intrigue. Observations from the Los Cumbres Observatory showed that the star not only dims erratically, but also seems to be undergoing a long-term secular dimming. Analysis of historical photographic plates from Harvard dating back to the 19th century suggested that Tabby's star may have faded by as much as 15% over the past century. This added a whole new layer to the puzzle, implying that whatever is blocking its light is not just a transient event, but a process that has been unfolding for a very long time. More recent studies have begun to shed light, literally, on the mystery. Detailed spectroscopic analysis has revealed that the star's light is being dimmed differently across various colors. It dims more in blue light than in red light. This is a classic signature of scattering by dust grains. Small particles of dust are very effective at blocking blue light while allowing redder light to pass through, much like our own atmosphere makes the sun appear red at sunset. This finding strongly points towards a natural explanation involving circumstellar dust, likely in a giant, uneven ring or disk around the star, perhaps the aftermath of a catastrophic planetary collision or a period of intense comet bombardment. Yet, even this more grounded theory has its complications. The dust would need to be on very eccentric orbits to explain the irregularity of the dips, and we still lack a complete model that can reproduce the full range of the star's bizarre photometric behavior. The long-term fading also remains a challenge to explain, as the dust from a single collision should eventually dissipate or fall into the star. So, where does that leave us with Tabby's star? It remains one of the most compelling and open cases in modern astronomy, a celestial object that has successfully humbled our models of stellar systems. It has forced us to confront the limits of our knowledge and to consider phenomena we never thought possible, from planetary-scale collisions to the faint, speculative signature of intelligence among the stars. Its greatest legacy may not be a definitive answer, but the paradigm shift it has inspired. It has shown that the hunt for extraterrestrial intelligence is not just about listening for radio signals, but also about scanning the heavens for astrophysical anomalies, for engineering on a scale so vast that it alters the appearance of a star itself. Tabby's star stands as a permanent reminder that our universe is capable of producing wonders that defy our immediate comprehension, pushing us to keep looking, keep questioning, and keep wondering what other impossible things are waiting to be found in the starlight. While we search for answers among distant stars and cosmic anomalies, one of the most breathtaking geometric puzzles is actually spinning in our own celestial backyard, adorning the crown of a gas giant. High above Saturn's North Pole, a storm of almost unimaginable scale rages, but it is a storm of remarkable order, not chaos. This is the Great White Hexagon, a six-sided jet stream that wraps around the planet's pole like a colossal, rotating honeycomb cell. What makes this feature so profoundly defying is its sheer persistence and geometric perfection. In the turbulent, gaseous atmospheres of planets, nature tends to favor two forms, either the chaotic, swirling maelstrom of a vortex, like Jupiter's Great Red Spot, or the messy, turbulent flows of a standard jet stream. A stable, polygonal shape with six distinct, razor-sharp sides is not just unusual. According to our standard models of fluid dynamics, it is virtually an impossibility. Yet there it is, a perfect hexagon large enough to comfortably contain four Earths side by side, and it has been there, churning away, for every single observation we have made since its discovery. The story of its discovery is a testament to the patient, piece-by-piece exploration of our solar system. While hints of something strange at Saturn's pole were seen in the Voyager flybys in the early 1980s, the full, breathtaking geometry of the hexagon wasn't revealed until decades later. The Cassini spacecraft, which entered orbit around Saturn in 2004, provided the first clear, stunning images. Unlike the southern pole, which hosted a more conventional, swirling hurricane, the North Pole was enclosed by this precise, six-sided wall of clouds. The sides of the hexagon are not faint suggestions, they are towering walls of cloud, each one an active jet stream where winds scream at speeds over 300 miles per hour. The entire structure rotates with a period of about 10 hours and 30 minutes, acting like a single, massive, rigid body despite being composed of nothing but gas. The most mind-bending part is its longevity. When it was first clearly observed by Cassini, scientists initially wondered if it was a transient feature. But as the years turned into a full Saturnian season equivalent to over 7 Earth years, the hexagon remained steadfast and unchanging. Given its stability, it is entirely possible this atmospheric titan has been spinning for centuries, a permanent, sculpted feature on a world without a solid surface. So, how does a planet create and, more importantly, maintain such a bizarre structure? The hunt for an answer has moved from the rings of Saturn down into laboratories and supercomputers on Earth. Fluid dynamicists who study how liquids and gases flow were immediately captivated. The key to the mystery lies in something known as a zonally propagating jet stream. Imagine a rotating cylinder like a soup can filled with water. If you spin the can and then rotate a small disk at the bottom, you can simulate the different rotational forces at work in a planetary atmosphere. In experiments that do just this, scientists have been able to produce polygonal shapes, including stable ovals, triangles, and yes, hexagons. The shapes form at the boundary between different latitudinal bands, where there is a sharp gradient in the speed of the flowing fluid. On a giant, rapidly rotating planet like Saturn, the deep atmosphere may act like this rotating fluid, and the hexagon appears to be a standing wave pattern, a giant, stable ripple frozen in the atmosphere's jet stream. It is not a solid structure, but a self-organizing pattern of turbulence, a case where chaos and instability somehow give rise to a perfect, enduring order. Computer simulations have taken this laboratory work even further, modeling the complex physics of Saturn's deep atmosphere. These models suggest that the hexagon is likely a manifestation of a phenomenon where a deep, rotating jet stream becomes unstable to certain types of waves. Specifically, a type of wave known as a Rossby wave can become trapped at a particular latitude. Under the right conditions, the interference pattern of these waves can create a stable, polygonal shape. The number of sides is thought to be determined by the characteristics of the jet stream itself, its speed, width, and the rate of the planet's rotation. For Saturn's north polar jet, the specific combination of these factors seems to favor a six-sided pattern. This makes the hexagon less of a static object and more like a song being sung by the atmosphere, with the jet stream's properties setting the pitch and the planet's rotation providing the rhythm, resulting in a harmonic that takes a geometric form. What is still a subject of intense study is why this pattern is so incredibly stable and long-lived, while similar features in lab experiments are often fleeting. The answer may lie in the immense scale and energy of Saturn's weather systems, which operate on a level that dwarfs anything we can replicate on Earth. The enduring defiance of the Saturn hexagon offers a humbling lesson. Here is a phenomenon that is not hidden in deep space or composed of invisible matter. It is a vast, visible, and stunningly beautiful feature on a planet we have visited with our robots. Yet, its very existence challenges the textbooks on fluid dynamics, forcing us to expand our understanding of how order can spontaneously emerge from chaos. It shows us that even the most fundamental processes in nature can still surprise us, creating patterns of such mathematical purity that they seem almost engineered. As we continue to study this atmospheric marvel, it serves as a constant reminder that the solar system is still a place of profound mystery, where even the weather on our planetary neighbors can hold secrets that defy our expectations and inspire a deeper sense of wonder about the intricate physics that sculpt our cosmic neighborhood. From a perfect hexagon spinning on a neighboring planet, we now travel back in time to our own world, to a period when our planet's very existence seemed to defy the basic logic of astrophysics. This is the faint young sun paradox, a puzzle that pits our understanding of stellar evolution directly against the geological evidence of our own ancient Earth. Here's the problem in its starkest terms. We know from robust models of how stars work that our sun, like all stars of its type, has been gradually growing brighter over its lifetime. Billions of years ago, when life was first taking hold on Earth, the sun was significantly fainter, about 25 to 30% less luminous than it is today. If you take our present-day Earth and simply dim the sun by that much in a climate model, you get one result, and one result only: a global, deep frozen ball of ice. The entire planet, from the poles to the equator, should have been locked in a permanent snowball Earth state with average temperatures far below freezing. The oceans should have been mile-thick ice and the land buried under glaciers. Yet, when geologists examine the most ancient rocks on our planet, they find a completely different story written in stone. The evidence is undeniable and comes in several forms. Among the oldest sedimentary rocks known, like the Isua Greenstone Belt in Greenland, which dates back over 3.8 billion years, we find layers that were clearly deposited in liquid water. You don't get finely layered sediments or certain types of rippled patterns from ice. You get them from flowing rivers, waves on a shoreline, or settling at the bottom of a sea. Even more compelling is the presence of pillow basalts, volcanic rock formations that only take shape when lava erupts directly under a deep ocean. This is conclusive proof that vast, open bodies of liquid water existed on the surface of the Earth at a time when, according to the astrophysics, our world should have been an ice cube hurtling through space. The most dramatic evidence, however, comes from the cradle of life itself. Fossilized stromatolites, which are layered structures formed by colonies of ancient microbes, have been found in rocks over 3.4 billion years old. Life not only existed, it was thriving in shallow, sunlit waters. The contradiction could not be more profound. A faint sun points to a frozen, dead world. Our geological record shows a watery, living one. Something, or some combination of things, had to be keeping the early Earth warm against all odds. This paradox forces us to look at Earth's own ancient systems, and the most prominent solution points squarely at the planet's early atmosphere. Our air today is a delicate mix of nitrogen and oxygen, with just a trace of carbon dioxide and other greenhouse gases providing a critical, life-sustaining blanket. The early Earth's atmosphere, however, was a completely different beast, likely rich in powerful greenhouse gases that have since diminished. One leading candidate is carbon dioxide. Geological processes, particularly the weathering of silicate rocks, pull carbon dioxide out of the atmosphere over long timescales. It's possible that in Earth's youth, volcanic outgassing was pumping carbon dioxide into the air far faster than it could be removed, creating a dense, heat-trapping cloak. Models suggest that the carbon dioxide levels would have needed to be hundreds or even thousands of times higher than they are today to compensate for the faint sun, a truly alien and oppressive atmosphere. Another, even more potent player was almost certainly methane. Produced by early methanogenic microbes, methane is a greenhouse gas dozens of times more effective than carbon dioxide at trapping heat. A combination of high carbon dioxide from geology and high methane from biology could have created a super-powered greenhouse effect, turning a planetary deep freeze into a temperate, if somewhat strange and hazy, nursery for life. But the atmosphere might not be the whole story. Scientists have also proposed that the Earth itself was spinning faster in its youth, with days that were significantly shorter. A faster rotation alters global wind patterns and cloud cover. Some climate models suggest that with shorter days, clouds might have clustered more over the tropics, making them brighter and more reflective, which would cool the planet. However, other models indicate that faster rotation could reduce overall cloud cover in the mid-latitudes, allowing more sunlight to reach the surface and warm it. The interplay is complex, and it's an active area of research, showing that even fundamental planetary characteristics like the length of a day can play a role in solving this ancient climate puzzle. Another fascinating idea involves the appearance of the Earth itself. Today, our planet has bright, reflective ice caps at the poles. A frozen snowball Earth would be incredibly bright, reflecting most sunlight back into space and locking in the cold. But a largely ice-free early Earth with dark ocean water covering most of its surface would have been much darker and absorbed a great deal more of the sun's faint energy. This lower albedo or reflectivity could have provided a crucial few extra degrees of warmth, helping to tip the balance away from a global glaciation. The resolution to the faint young sun paradox likely lies not in one single magical solution, but in a combination of these factors. A thicker blanket of greenhouse gases, a different atmospheric composition, a faster spinning planet, and a darker surface, all working in concert to create a fragile yet stable, warm climate. This mystery is more than just a historical curiosity about our planet. It's a profound lesson in planetary science. It shows us that a world's climate is an incredibly complex and resilient system, with multiple knobs and dials that can be adjusted to maintain habitability even under stellar conditions that seem, at first glance, utterly hostile to life. As we look out at other worlds orbiting other stars, many of which are younger and fainter than our Sun, the solution to this paradox gives us hope. It suggests that the habitable zone around a star might be wider and more forgiving than a simple calculation of starlight would imply, and that a planet's own atmosphere and geology can play a heroic role in writing its own story of life against the cosmic odds. But if Saturn's hexagon represents a defiance of atmospheric physics, our next encounter was with a visitor that seemed to defy classification itself, an object from the deep void between stars that challenged our very definitions of what a celestial body can be. In October 2017, astronomers at the Pan-STARRS Observatory in Hawaii spotted a faint point of light moving at a speed so high it could only mean one thing: it was not from here. This was Oumuamua, a name from Hawaiian meaning a messenger from afar arriving first, and it was the first object ever detected from interstellar space, a cosmic wanderer passing through our solar system. The initial excitement was electric, but as more data was gathered, that excitement quickly morphed into profound bewilderment. Oumuamua wasn't just an oddity, it was an anomaly in motion, a collection of properties so strange that it left scientists with more questions than answers. The first puzzle was its shape. By carefully analyzing how its brightness changed over time, astronomers could infer its rotation, and the resulting light curve was bizarre. It suggested an object that was dramatically elongated, tumbling end over end through space. The best fit model indicated a shape unlike anything we have in our own solar system, a highly elongated cigar, or as later data suggested, an extremely flattened pancake. Its length was estimated to be somewhere between 5 and 10 times greater than its width. Imagine a flat, rocky pancake tumbling chaotically through the void. There is no known natural process in our solar system that creates asteroids or comets with such an extreme aspect ratio. The very form of this interstellar traveler was a challenge to our understanding of how small celestial bodies form and evolve. Then came the real mystery, the one that truly set Oumuamua apart and ignited a firestorm of scientific debate. As it traveled away from the Sun, having made its closest approach, astronomers were able to plot its trajectory with immense precision. They accounted for every known gravitational influence, the Sun, the planets, everything. Yet the path Oumuamua was taking didn't match the purely gravitational trajectory. It was experiencing a tiny but undeniable additional push. It was accelerating just slightly as it departed. This kind of non-gravitational acceleration is not unheard of. In fact, it's common for comets. When a comet's icy surface is heated by the Sun, it sublimates, turning directly from ice to gas. This outgassing creates jets that act like tiny thrusters, pushing the comet and altering its orbit in a way that pure gravity cannot explain. The problem with Oumuamua was that it showed absolutely no signs of this outgassing. No visible coma, the fuzzy envelope of gas and dust that surrounds a comet's nucleus, no tail streaming away from the Sun. Our most sensitive telescopes, including the Hubble Space Telescope, scanned it intently and found zero evidence of the dust or gas molecules that would be the undeniable signature of a comet. It was accelerating as if it were a comet, but it looked for all the world like a barren, inactive asteroid. This was the central, glaring defiance, an effect without a visible cause. The scientific community scrambled for natural explanations, leading to some truly ingenious and exotic proposals. One prominent theory suggested that Oumuamua was in fact a comet after all, but one made of something more exotic than the usual water ice. Perhaps it was composed largely of solid molecular hydrogen or solid nitrogen. A hydrogen iceberg, for instance, could sublimate under sunlight, providing the necessary push. Because hydrogen gas is invisible to our telescopes at those densities, it would explain the acceleration without a visible coma. The same could be true for a chunk of nitrogen ice, similar to what is found on the surface of Pluto. However, these ideas came with their own significant hurdles. The stability of a pure hydrogen iceberg in interstellar space is questionable, as it would likely evaporate too quickly. And the amount of nitrogen ice required to form such an object would be staggering, potentially requiring the shattering of a Pluto-like world in another star system, an event that is statistically very rare. While creative, these natural explanations felt like forcing a square peg into a round hole, requiring a series of special conditions to align perfectly. It was this very lack of a comfortable, conventional explanation that opened the door to a more radical and highly controversial hypothesis put forward by Harvard astronomer Avi Loeb. He and a colleague proposed that the anomalous acceleration could be explained if Oumuamua was not a natural object at all, but a piece of advanced alien technology, specifically a light sail. A light sail is a proposed form of spacecraft propulsion that uses the tiny but constant pressure of sunlight for thrust. A large, incredibly thin and reflective sheet could be pushed by photons from a star, just as Oumuamua was. This would account for the non-gravitational acceleration without the need for any outgassing. The object's unusual, flattened shape would also be consistent with the design of a light sail, and its unusual brightness variations could be explained by its tumbling motion. Loeb argued that we should seriously consider the possibility that we had just witnessed a piece of discarded extraterrestrial machinery, a derelict probe or a fragment of a larger vessel drifting through our cosmic neighborhood. The scientific community largely remained skeptical, rightly pointing out that an extraordinary claim requires extraordinary evidence, and that we should exhaust all natural explanations before leaping to an artificial one. Yet, the very fact that such a proposal could be seriously debated in a scientific journal underscored just how deeply Oumuamua had challenged our paradigms. The legacy of Oumuamua is not that it proved the existence of aliens because it did no such thing. Its true, enduring significance lies in the profound questions it forced us to ask about the nature of objects traveling between stars. It revealed a glaring gap in our knowledge. Before its visit, our models of planetary formation suggested that interstellar space should be filled with rocky asteroids ejected from their home systems. Oumuamua's comet-like behavior without the classic cometary features turned that simple assumption on its head. It showed us that the building blocks of other planetary systems might be made of materials and operate by rules we have not yet anticipated. Its fleeting passage was a tantalizing, frustrating glimpse into the incredible diversity of the galaxy, a single data point that screamed that our solar system is not the template for all others. The object is now long gone, too faint and too distant to ever be observed again, leaving behind only a trail of data and a powerful reminder that the universe is under no obligation to conform to our textbooks. It challenges us to build better telescopes like the forthcoming Vera-C, Rubin Observatory, which will scan the entire sky nightly, ensuring that the next interstellar messenger will not slip by unnoticed and that we might finally get a clearer look at the strange travelers from distant suns. We've journeyed past interstellar wanderers and planetary weather patterns, but now we must confront a force so subtle and pervasive that it weaves through the very fabric of galaxies, shaping them in ways we are only beginning to grasp. This is the enigma of galactic magnetic fields. Look at any spiral galaxy, and you'll see majestic arms painted with the light of billions of stars. But what you can't see is the invisible scaffolding of magnetism that fills the space between them. These are not weak, messy fields either. They are large-scale, surprisingly organized structures that can stretch for tens of thousands of light years, guiding cosmic rays, influencing the birth of stars, and leaving their imprint on the light that passes through them. The central puzzle is not that these fields exist, but how they can possibly be so strong and so coherent across such unimaginable distances, especially when our best theories suggest they should have faded into nothingness eons ago. To understand why this is so baffling, we need to think about how magnetic fields usually behave. A fundamental principle of electromagnetism is that magnetic fields in a plasma, a hot, ionized gas like the material between stars, are not supposed to last forever on their own. They decay, and they do so relatively quickly. In the diffuse, turbulent medium of a galaxy, calculations suggest that any primordial magnetic field, one left over from the galaxy's formation, should have dissipated due to a process called resistive decay in just a few 100 million years. That's a blink of an eye on a cosmic timescale. Our own Milky Way is over 13 billion years old. If these fields were simply fossils from the distant past, they should have vanished dozens of times over. Their persistent presence today is a clear signal that something is actively generating and maintaining them, a cosmic engine that is constantly at work, fighting against the natural tendency of these forces to fade away. The leading theory for this cosmic regeneration is known as the galactic dynamo. Think of it as a gigantic, galaxy-sized version of the dynamo in a bicycle light. In that small device, the rotation of a coil of wire within a magnetic field generates an electrical current, which in turn amplifies the magnetic field. On a galactic scale, the ingredients are the galaxy's rotation, its turbulent interstellar gas, and a tiny seed magnetic field to start with. The theory proposes that the differential rotation of the galaxy, where the inner parts orbit the center faster than the outer parts, stretches and shears this weak seed field, winding it up like a spool of thread. At the same time, the churning turbulence from supernova explosions and stellar winds twists this wound-up field, folding it back on itself in a way that reinforces and amplifies the original magnetic field. This self-sustaining loop of motions, if it works perfectly, could theoretically take a vanishingly weak initial field and pump it up to the strengths we observe today. However, this elegant theory is fraught with immense challenges that leave many scientists unconvinced it tells the whole story. For one, the galactic dynamo is an incredibly delicate and slow process. The initial seed field required is a critical unknown. Where did it come from? Was it generated in the early universe before galaxies formed, perhaps from processes in the primordial plasma? Or was it created by the first stars and galaxies themselves? Furthermore, computer simulations of galactic dynamos struggle to produce the kind of large-scale, ordered fields we see. The turbulence of the interstellar medium is so violent and chaotic that it often tangles and randomizes the magnetic field lines faster than the orderly rotation can align them. The dynamo models often predict fields that are far more messy and disordered than the remarkably coherent structures we detect threading through galactic arms. It's like trying to braid a rope in the middle of a hurricane. The forces of chaos constantly threaten to undo any organized pattern. The observational evidence only deepens the mystery. When astronomers measure these galactic fields, primarily by observing the polarization of starlight and radio waves as they pass through the magnetized interstellar dust, they find fields that are not only strong but also astonishingly well-ordered. In many spiral galaxies, the magnetic field neatly follows the spiral structure of the arms themselves. This degree of organization is incredibly difficult for dynamo models to replicate. It suggests that the magnetic fields are not just a passive byproduct of galactic motion, but an active and integral component of the galaxy's structure and evolution. They may play a crucial role in channeling gas flows, regulating the formation of new stars, and even confining the high-energy cosmic rays that zip through interstellar space. The fields seem to be in a dynamic equilibrium with the galaxy itself, a partnership that our current models of magnetohydrodynamics, the physics of how magnetic fields and plasmas interact, struggle to fully capture. This gap in our understanding points to the possibility that we are missing a key piece of physics in our description of cosmic magnetism. Perhaps the seed fields were imprinted in the universe's infancy with a specific strength and configuration that gave the dynamo a crucial head start. Or maybe there are amplification mechanisms we haven't yet considered, involving the vast halos of galaxies or the interactions between galaxies in clusters. Some researchers even speculate that more exotic physics, related to the nature of dark matter or the behavior of plasmas in conditions we cannot replicate on Earth, could be at play. The persistence of these powerful, organized magnetic fields across billions of years and thousands of light years stands as a quiet but monumental defiance of our simplistic models. It reveals a galaxy not just as a collection of stars and gas, but as a complex electromagnetic entity whose hidden forces continue to challenge our grasp of one of the universe's most fundamental powers. Now, let's return to that cosmic speed limit we touched on earlier, the GZK cutoff, and meet one of the most legendary rule breakers ever recorded, a single particle so energetic and so baffling that it earned a name worthy of pure astonishment. On the 15th of October 1991, the Fly's Eye cosmic ray detector in the Utah desert registered an event that sent shockwaves through the world of physics. It wasn't a flashy explosion or a slow-building anomaly. It was the impact of a single, solitary atomic nucleus, most likely a proton, striking the upper atmosphere. But this was no ordinary particle. When the scientists calculated its energy, the result was so staggering that it seemed to defy reality itself. They called it the "Oh my God" particle, a name born from the sheer, spontaneous exclamation of disbelief it inspired. This one subatomic speck possessed a kinetic energy of about 300 quintillion electron volts. To put that inconceivable number into perspective, this single proton was carrying the energy of a professionally thrown baseball, all compressed into a space a trillion times smaller than a grain of sand. It was millions of times more powerful than anything we can produce in the most advanced particle accelerators on Earth. A lone messenger from the cosmos that arrived with an energy that should not have been possible after a long journey through space. This is where the GZK cutoff becomes so critically important. Remember, this theoretical limit, named for Greisen, Zatsepin, and Kuzmin, acts as a cosmic roadblock for such ultra-high energy particles. The space between galaxies is not a perfect vacuum. It is filled with the faint, cold photons of the cosmic microwave background, the relic radiation from the Big Bang. For a proton traveling at over 99.9999% the speed of light, these otherwise harmless background photons are transformed into a relentless barrage of high-energy gamma rays. Each collision between the ultra-fast proton and a background photon should sap its energy, producing other particles in a process that acts like a constant, universal braking mechanism. Over a distance of more than 150 million light-years, this energy loss should be total, imposing a strict upper limit on the energy of any cosmic ray that reaches us from beyond our local cosmic neighborhood. The Oh My God particle and a handful of others like it detected since didn't just nudge past this limit. They smashed through it with unimaginable force, arriving with energies that the GZK process should have drained away billions of years ago. The immediate and most logical conclusion is that these particles must be coming from somewhere relatively close by, cosmically speaking. If their origin is within that 150 million light-year GZK horizon, they wouldn't have had enough travel time to be significantly slowed down by interactions with the cosmic microwave background. This, however, replaces one profound mystery with another, launching an immense cosmic treasure hunt. When astronomers traced the rough incoming direction of the Oh My God particle and other similar ultra-high-energy events, they pointed back to seemingly empty patches of sky. There was no brilliant quasar, no violently active galaxy, no cataclysmic gamma-ray burst remnant in the vicinity. It was as if a cannonball had been fired into a crowd from point-blank range, but when everyone turned to look, there was no cannon. The defiance here is twofold. First, our understanding of particle physics is challenged by the particle's sheer energy, and second, our knowledge of cosmic geography is challenged by the apparent lack of any source powerful enough to have launched it. So what kind of cosmic engine could possibly create such an unimaginable particle? The candidates proposed by theorists are as extreme as the phenomenon itself. One leading possibility is an active galactic nucleus where a supermassive black hole weighing billions of times our sun's mass is actively feeding. The intense magnetic fields in the relativistic jets that scream away from these monsters could, in theory, act as a natural particle accelerator of almost limitless power. Another candidate is a gamma-ray burst, the single most energetic type of explosion known to occur in the universe, which for a few brief seconds can outshine an entire galaxy. The shockwaves from such an event could potentially accelerate particles to these ridiculous energies. Some have even considered more exotic sources, like the decay of super-heavy dark matter particles from the early universe or cosmic strings, hypothetical topological defects in spacetime itself. Yet for each of these brilliant proposals, there is a significant catch. Active galactic nuclei and gamma-ray bursts are spectacularly luminous. We should be able to see them. The fact that we don't see a clear, obvious source in the direction of these ultra-high-energy cosmic rays is a major part of the puzzle, suggesting that either these sources are hidden in some way or our models of how they accelerate particles are fundamentally incomplete. This mystery is compounded by a fiendish problem. These particles are charged. Protons and atomic nuclei carry an electric charge, which means their paths are not straight lines through the universe. They are constantly bent and scrambled by the weak but pervasive magnetic fields that fill the interstellar and intergalactic medium. By the time one of these particles finally reaches Earth, its trajectory has been twisted and turned so many times that its original direction of travel is completely lost. It's like trying to find the source of a river by looking at a single drop of water after it has passed through a complex network of swirling canals and whirlpools. This magnetic scrambling makes it incredibly difficult to pinpoint a source on the sky, turning a precise pointer into a fuzzy, uncertain blur. This is why, despite decades of searching with increasingly sophisticated observatories like the Pierre-Auger Observatory, we still cannot definitively say where the oh my god particle came from. The violation of the GZK cutoff is not just a theoretical curiosity. It is a practical, observational dead end that forces us to question whether we truly understand the most powerful accelerators in the cosmos, or if there is an entirely new class of astrophysical object, dark and silent, capable of hurling such incredible projectiles across the universe. But as we grapple with the sources of unimaginable cosmic rays, a different kind of tension has been quietly building, one that strikes at the very heart of our understanding of cosmic evolution. This is the Hubble tension, and it represents a crisis not of energy, but of speed specifically, the speed at which the universe is expanding. For decades, astronomers have worked to pin down the exact value of the Hubble constant, a single, crucial number that describes the current expansion rate of the cosmos. It's the ultimate cosmic speedometer. The unsettling reality we now face is that we have two supremely precise and sophisticated methods for measuring this rate, and they are giving us two different, stubbornly incompatible answers. It's as if you used two different, perfectly calibrated radar guns to measure the speed of the same car, and one told you it was going 60 miles per hour while the other insisted it was going 70. The difference isn't a small, negligible error bar. It's a significant and growing discrepancy that refuses to go away, suggesting that our fundamental model of the universe might be missing a critical ingredient. To understand why this is such a profound problem, we need to look at these two competing measurement techniques. The first method acts as a cosmic archaeologist, peering back in time to the universe's infancy. This approach uses the exquisitely detailed map of the cosmic microwave background provided by the Planck satellite. This ancient light, released when the universe was just 380,000 years old, shows us the precise lumpiness of the early cosmos, the seeds of all future galaxies. By plugging these measurements into the standard model of cosmology, known as lambda cold dark matter, we can run the cosmic film forward in time. The model, which includes the effects of dark matter and dark energy, predicts exactly how fast the universe should be expanding today. This early universe method gives us a very precise but indirect measurement of the Hubble constant. The result from Planck is a relatively sedate 67.4 kilometers per second per megaparsec. In simpler terms, this means that for every million parsecs of distance, a parsec being about 3.26 million light-years, a galaxy is receding from us at 67.4 kilometers per second. The second method is more like a modern-day surveyor taking measurements in our local cosmic neighborhood. This late universe technique relies on a series of meticulously calibrated cosmic distance ladders. It starts with parallax measurements to nearby stars, the most fundamental way to gauge distance in space. From there, astronomers use a special class of stars called Cephid variables as their next rung. These stars pulsate with a regular rhythm, and the period of their pulsation is directly related to their true intrinsic brightness. By measuring how bright they appear from Earth and knowing how bright they actually are, we can calculate their distance with remarkable accuracy. Cephids then help calibrate the brightness of Type Ia supernova, those brilliant standard candles that allow us to measure distances to faraway galaxies. When you combine all these steps, parallax, Cephids, and supernova, you get a direct local measurement of how fast those galaxies are moving away from us right now. The teams using this method, most notably the SH0ES collaboration, have relentlessly refined their measurements, and they consistently arrive at a faster, more frenetic expansion rate, around 73 kilometers per second per megaparsec. The problem is that these two numbers, 67 and 73, are decisively and statistically in disagreement. Their error bars, the range of uncertainty for each measurement, no longer overlap. This isn't a case of sloppy science. In fact, it's the opposite. Both methods have been honed to an incredible degree of precision, with uncertainties now down to just 1 or 2%. The more we improve our measurements, the more the discrepancy solidifies, transforming from a minor worry into a full-blown crisis for cosmology. This Hubble tension is so serious because it pits two pillars of modern astronomy against each other. One is our understanding of the very early universe, encoded in the pristine cosmic microwave background. The other is our understanding of stellar physics and the local cosmos, built on a century of painstaking observational work. They can't both be completely correct within our current standard model. One of our most trusted cosmic yardsticks appears to be broken, or worse, our model of the universe's contents and history is fundamentally flawed. This persistent defiance has forced cosmologists to consider truly exotic possibilities that lie beyond our established theories. Perhaps dark energy, the mysterious force driving cosmic acceleration, is not a constant as Einstein proposed, but something that evolves over time. This dynamic dark energy, sometimes called quintessence, could have strengthened in the more recent epoch of the universe, giving an extra kick to the expansion and explaining why our local measurements show a faster rate than the early universe data predicts. Another compelling idea involves a previously unknown type of relativistic particle that flooded the universe in its first few 100,000 years. These could be sterile neutrinos, ghostly particles that interact only through gravity. Their presence would have altered how the early universe evolved, changing the sound waves imprinted on the cosmic microwave background, and consequently, the predicted value of the Hubble constant derived from it. A third, more dramatic proposal suggests that the elusive dark matter, which makes up most of the universe's matter, might have properties we never anticipated. Maybe dark matter particles can interact with each other or with dark energy in ways that subtly change the growth of cosmic structures, creating a disconnect between the early and late expansion histories. Each of these proposals is a testament to the creativity of scientists facing a major puzzle, but each one also comes with its own challenges, often disrupting other beautifully confirmed aspects of the cosmological model. The Hubble tension, therefore, is more than just a number dispute. It is a powerful beacon, illuminating the potential for a seismic shift in our understanding of the cosmos, pointing toward a new chapter in physics that we have only just begun to imagine. Buried deep within the oldest light in the universe is a chill that shouldn't be there, a cosmic cold spot so vast and improbable it has astronomers questioning if we are truly alone in the cosmos, not in the sense of life, but in the very nature of reality itself. This is the mystery of the CMB cold spot, a colossal patch in the cosmic microwave background that is significantly colder than its surroundings. To call it a spot is a dramatic understatement. It spans a region of sky nearly 1 billion light-years across, a staggering void in the fabric of the universe that defies the standard, random fluctuations we expect from the Big Bang's afterglow. The probability of such an extreme feature arising by pure chance in our standard cosmological model is astronomically low, something like 1 in 200. It's an anomaly on a truly grand scale, a cosmic bruise that hints at a violent event or a fundamental flaw in our understanding of the universe's infancy. When scientists first noticed this peculiar cold region in data from the Wilkinson microwave anisotropy probe, they immediately looked for the most straightforward explanation. The leading hypothesis was that we were looking at a vast supervoid, an enormous region of space with a dramatically lower density of galaxies, galaxy clusters, and even dark matter than the cosmic average. The physics of how a supervoid could cause a cold spot is a fascinating dance of cosmic energy. As light from the CMB travels across the universe toward us, it passes through various gravitational fields. When this light enters a massive structure like a galaxy cluster, it gains energy as it falls into the cluster's gravitational well, making it appear slightly hotter. Then, as it climbs out the other side, it loses that energy again. In a standard, static universe, these effects would cancel out, but our universe is expanding. As light enters a vast, underdense region like a supervoid, it loses energy climbing out of the shallow gravitational well. And because the universe has expanded during its long journey through the void, it doesn't get all that energy back when it exits. This integrated Sachs-Wolf effect results in a net loss of energy, making the CMB light that passed through the void appear cooler to our telescopes. It's a subtle but measurable effect, and a supervoid of the right size and emptiness could, in theory, produce the cold spot we observe. The hunt was on to find this predicted supervoid. Astronomers began meticulously mapping the galaxy distribution in the direction of the cold spot, expecting to find a corresponding emptiness of epic proportions. The results, however, were deeply puzzling. They did find a void now known as the Eridanus supervoid, but it was not nearly as vast or as empty as the cold spot theory required. The supervoid is large, certainly, but its observed depth and size can only account for about 10% of the temperature drop seen in the CMB. It's as if doctors found a tiny, shallow scratch on a patient who was suffering from a massive, life-threatening wound. The two are related, but the minor injury cannot possibly explain the severity of the trauma. This mismatch between the observed underdensity and the required one to explain the cold spot's intense chill created a crisis. If a supervoid isn't the culprit, then what kind of cosmic phenomenon could leave such a frigid imprint on the dawn of time? It is this failure of the conventional explanation that opens the door to possibilities that sound like they are ripped from the pages of a theoretical physics textbook. One of the most mind-bending proposals is that the cold spot is evidence of a cosmic collision, a bruise left from an impact with another universe. This idea emerges from the theory of eternal inflation and the multiverse. In this framework, our entire observable universe is just one bubble in a vast, frothing cosmic foam of infinite universes, each with its own distinct physical laws. According to this theory, these bubble universes can sometimes collide as they expand within the greater multiverse. If a neighboring bubble universe brushed against our own in the distant past, during or shortly after inflation, the energy released at the boundary of that collision could have created a specific signature in the CMB. The physics of such an event would be unlike anything within our universe, potentially creating a region that appears anomalously cold. In this radical interpretation, the cold spot is not a feature of our universe at all, but a window into the cosmos beyond our cosmic horizon, a fossilized imprint of a long-ago encounter with another reality entirely. Of course, such a spectacular claim requires scientists to explore every other conceivable alternative. Other, less extreme but still exotic, ideas have been put forward. Perhaps the cold spot is not a physical structure in space, but a manifestation of a non-trivial topology of the universe itself. If the cosmos is finite and has a complex shape like a hall of mirrors on a cosmic scale, the light from the CMB could have taken multiple paths to reach us, creating overlapping patterns that include unexpected cold regions through a kind of cosmic lensing effect we don't fully understand. Others have suggested it could be the shadow of a colossal, pre-inflationary defect in spacetime, a remnant from the first fractions of a second after the Big Bang, like a cosmic texture or a magnetic monopole of unimaginable scale. Yet, each of these explanations, while fascinating, remains highly speculative, lacking the direct evidence that would elevate it from a compelling hypothesis to an established theory. The enduring power of the CMB cold spot mystery lies in its stubborn refusal to be easily categorized. It stands as a monument to the limits of our current knowledge, a ghostly patch on the map of creation that whispers of physics operating on scales and in realms we can scarcely imagine. Whether it is ultimately explained by an unusual configuration of dark energy, a statistical fluke of a scale we've never seen before, or something as profound as a multiverse collision, its very existence forces us to confront the humbling reality that our universe is far stranger and more complex than our standard models suggest. It is a celestial cipher, a riddle written in the cold, and its solution may very well require us to rewrite our most fundamental stories of how everything began. And just when the steady glow of the cosmic microwave background had lulled us into a sense of ancient, predictable calm, the universe decided to unleash a phenomenon of such brief, violent intensity that it redefined the very meaning of the word flash. These are fast radio bursts, or FRB, and they are among the most electrifying and mysterious events in the modern cosmos. Imagine a single, brilliant burst of radio light, a scream of energy that lasts for just a few thousandths of a second, shorter than the blink of an eye. In that fleeting instant, this burst can release more energy than our sun puts out over an entire month, sometimes even decades. It is a cosmic flashbulb popping from billions of light years away, and for years after the first one was discovered in archived data from 2007, astronomers were utterly baffled. Was it a one-time catastrophic event, a glitch in our instruments, or was it something else entirely, a new class of astronomical object that operated on a timescale and with a power we had never before witnessed? The plot thickened dramatically with the discovery of repeating FRBs. The first of these, known as FRB 1211-2, shattered the assumption that all such bursts were singular, self-destructing cataclysms. This one source, located in a dwarf galaxy 3 billion light-years away, would occasionally fire off another burst and then another with no discernible pattern. It wasn't dead, it was dormant, an engine that could turn itself on and off again at random intervals. This single discovery cleaved the mystery of FRBs in two, forcing scientists to confront the reality that there must be at least two different kinds of sources, one that produces a single, immensely powerful burst, and another that can somehow survive its own outburst and produce multiple eruptions over time. The repeaters, with their unpredictable, sputtering nature, ruled out any theory that required the complete annihilation of the source, such as the merger of two neutron stars or the final collapse of a star into a black hole. Suddenly, the universe had presented us with not just a brilliant flash in the dark, but a blinking, unidentifiable beacon whose very existence challenged our catalogues of cosmic disasters. To grasp the sheer, defying power of these events, let's scale it down to something more relatable. Picture a typical radio station transmitter on Earth, broadcasting its signal across a city. Now, imagine a transmitter so powerful that its millisecond burst could be detected with perfect clarity from clear across the universe, billions of light-years away. The energy required for that is almost inconceivable. The leading natural suspects for such extreme engines are some of the most exotic objects known to science. At the top of the list are magnetars, a special class of neutron stars that possess the most powerful magnetic fields in the universe. A neutron star is the collapsed, ultra-dense core of a massive star that went supernova, and a magnetar is its supercharged, terrifying cousin. Its magnetic field is so intense that it could strip the information from every credit card on Earth from halfway across the solar system. The theory goes that these magnetars can experience starquakes, sudden fractures in their rigid, crystalline crust. These quakes release titanic amounts of pent-up magnetic energy, which could be focused into a jet of radio waves that we observe as an FRB. This model is particularly attractive for the repeating bursts, as a magnetar could experience multiple quakes over its lifetime. Supporting this, astronomers have even detected an extremely powerful FRB coming from within our own galaxy, sourced directly from a known magnetar, providing the first solid link between a specific object and one of these cosmic flashes. Yet, magnetars cannot explain every FRB, especially the non-repeating, seemingly one-off events. For these, the theories become even more dramatic. The collision and merger of two incredibly dense objects, like neutron stars or perhaps a neutron star and a black hole, could release a staggering amount of energy in a final, fatal burst of gravitational waves and radiation. This kind of event is cataclysmic and singular by its very nature. The source is utterly destroyed, which fits the profile of a non-repeating FRB perfectly. The immense energies involved in such a merger are certainly up to the task of powering these brilliant radio flashes. But even these apocalyptic scenarios are pushed to their limits by the most energetic FRBs we have recorded, leading some scientists to consider even more exotic possibilities. Could we be seeing the immense, focused energy release from a newborn black hole as it first turns on its jets? Or perhaps the eruption is caused by the snapping and reconnection of cosmic-scale magnetic field lines in the plasma surrounding a supermassive black hole. The speculative frontier of FRB research ventures into even more incredible territory. What if some of these signals, particularly the highly energetic, non-repeating ones, are not natural at all? The staggering power and brevity of FRBs have, much like the anomalies of Tabby's star, forced a responsible but open-minded consideration of artificial origins. Could an advanced civilization capable of engineering on an astronomical scale be using incredibly powerful pulsed beams for interstellar communication or to power light sails for their starships, just as we considered for Oumuamua? A directed energy beam used for propulsion would appear as a brilliant, fleeting flash to any observer who happened to be in its path, much like a lighthouse beam sweeping across a dark sea. While this is the least likely explanation and remains a last resort after all natural avenues are exhausted, the very fact that it can be seriously discussed in scientific circles underscores just how extreme and puzzling the fast radio burst phenomenon truly is. They are a perfect storm of mystery, unimaginably powerful, impossibly brief, and originating from the deepest reaches of space, forcing us to rewrite our understanding of the most violent and dynamic engines in the cosmos. Now, let's descend from the cosmic scale of colliding universes and fleeting radio bursts down to a quiet laboratory on Earth, where a different kind of defiance was brewing, one that threatened to overturn a law of physics so foundational that it feels as solid as the ground beneath our feet. This is the strange and controversial story of the M drive, or electromagnetic drive. In theory, it was a deceptively simple device, a hollow, truncated copper cone that you would pump full of microwaves. According to its proponents, simply bouncing these microwaves around inside the sealed chamber would magically produce a net thrust, a push in one direction without expelling any propellant whatsoever. If that sounds too good to be true, it's because it directly violates Newton's third law of motion, the principle of action and reaction. For every action, there is an equal and opposite reaction. This is why rockets work. They throw the hot gas from their engines backwards in order to propel themselves forward. The M drive claimed to achieve motion without throwing anything out the back. It was the ultimate cosmic free lunch, a device that promised to revolutionize space travel by allowing satellites to maneuver indefinitely and spacecraft to reach the stars, all without needing to carry vast, heavy tanks of fuel. The scientific uproar was immediate and intense, and for good reason. The conservation of momentum, which the M drive seemed to break, is not just some old idea. It's a cornerstone of physics that emerges directly from the fact that the laws of the universe are the same everywhere. To violate it would be to suggest that the universe has a preferred direction, a fundamental asymmetry that would ripple through our entire understanding of reality. The initial claims, primarily from a small team of researchers, were met with a wall of skepticism. But then something unexpected happened. Other groups, including a respected team at NASA Eagleworks Laboratory, began building their own versions of the M drive and testing it in sophisticated vacuum chambers, isolated from outside vibrations and magnetic fields. To the astonishment of many, they too reported measuring a tiny but persistent thrust. It was a minuscule force, just a few dozen micronewtons, about the weight of a single sesame seed on Earth. but it was a force that, according to every established law, should not have been there. The scientific community was thrown into a fascinating turmoil. Was this the crack in the dam, the first glimpse of a new physics that could unlock the stars? The controversy became a masterclass in how science grapples with an impossible result. Proponents of the drive scrambled to propose theoretical frameworks that could explain the anomaly without completely shattering physics. Some turned to the weirdness of quantum mechanics, suggesting that the microwaves were interacting with virtual particles popping in and out of existence in the quantum vacuum, effectively providing an invisible propellant. Others proposed modifications to Einstein's theory of inertia. These were fascinating, if highly speculative, ideas born from the desperate attempt to explain the data. Yet for every proposed theory, there were a dozen skeptical physicists who pointed out the fundamental problems. The most damning criticism was always the same: a propellantless drive is a perpetual motion machine for momentum. It would allow you to push against nothing, to generate a net force from within a closed box, a concept that is fundamentally at odds with our most deeply held principles. The resolution, as it so often does in these tales, came not from a grand new theory, but from increasingly careful and clever experimentation. The tiny thrust signal was a siren song, and researchers began a meticulous hunt for more mundane sources. The culprit, it turned out, was heat. When you pump thousands of watts of microwave power into a small copper cavity, it gets hot, very hot. This thermal expansion can cause tiny shifts in the device's center of mass. More critically, the heating of the air molecules still present in the vacuum chamber, or even the warming of the test apparatus itself, can create subtle currents of air or induce interactions with the Earth's magnetic field. One particularly elegant experiment in Germany used a highly sensitive pendulum balance and a new type of thrust balance that could distinguish between different types of forces. They ran the M drive and measured the familiar tiny thrust. Then they replaced the microwave power source with a simple resistive heater that dumped the exact same amount of thermal energy into the device without generating any microwaves at all. The result was definitive. The same tiny thrust appeared. The M drive effect was not coming from magical microwave physics. It was a classic, if subtle, thermal artifact. The thrust was being generated by the warm air molecules bouncing off the warmer end of the chamber with slightly more energy, a phenomenon known as the thermal Brownian effect. The universe hadn't broken a fundamental law. We had simply been tricked by one of its more mundane and persistent side effects. The legacy of the M drive is not one of revolutionary discovery, but it is a profoundly important one for the scientific process. It serves as a powerful, modern cautionary tale about the immense difficulty of measuring effects at the very edge of our instrumental sensitivity. It highlights the constant tension between the tantalizing allure of a world-changing breakthrough and the relentless, often unglamorous, work of ruling out every possible source of error. The story underscores why science moves slowly and cautiously, especially when faced with claims that defy its core tenets. It's a system built not to suppress new ideas, but to protect itself from the powerful human desire for those ideas to be true. In the end, the M drive did not give us the stars, but it did provide a valuable lesson in intellectual humility, reminding us that when an experiment seems to defy a fundamental law, the burden of proof is astronomically high, and the answer is almost always found not in rewriting the laws of physics, but in finding the hidden gremlin in the machine. From the cosmic scales of colliding galaxies and the explosive energy of fast radio bursts, we now plunge into a realm where the very act of observation seems to shape reality itself, a domain where the universe's defiance of scientific law becomes deeply personal and profoundly philosophical. This is the quantum suggestion of a conscious universe, a mystery that takes us from the precise, sterile environment of the laboratory directly to the heart of a question that has perplexed philosophers for millennia. Does reality exist independently of us, or do we, in some strange way, bring it into being through the very act of perceiving it? The story begins not with a telescope, but with a thought experiment involving a cat, a box, and a radioactive atom. An illustration so famous it has become a cultural touchstone for the bizarre nature of the quantum world. Erwin Schrödinger's cat is both alive and dead, sealed in a box with a poison trigger linked to the random decay of a single atom. According to the mathematics of quantum mechanics, until someone opens the box and looks inside, the atom exists in a blurred state of superposition. It has both decayed and not decayed simultaneously. Consequently, the unfortunate cat is suspended in a ghostly state, neither alive nor dead, but an unsettling mixture of both possibilities. This isn't just a metaphor. It's a direct consequence of the equations that describe the behavior of particles at the smallest scales, and it points to a reality that is fundamentally fuzzy and undefined until the moment it is measured. This leads us directly to the infamous measurement problem and the concept of wave function collapse. In the quantum realm, particles like electrons don't have definite properties like position or momentum until we measure them. Instead, they are described by a wave function, a mathematical expression that represents a smeared-out cloud of probability, a blueprint of all the places the particle could be and all the states it could be in. The truly baffling part is what happens when we set up a detector to find it. The moment we make a measurement, the wave function appears to collapse. The infinite set of possibilities vanishes and the particle snaps into a single, definite location, as if our looking at it forced it to make a choice. This is the role of the observer, and it is a role that seems to grant consciousness a peculiar and unsettling power. A Geiger counter-clicking is not enough. It's the conscious awareness of that click by a human mind that is often invoked as the final step that solidifies reality. The universe, at its most fundamental level, appears to be waiting for a witness. This idea shatters the clockwork, deterministic universe of Isaac Newton, where everything was predictable given enough information. In the quantum world, reality is not predetermined. It is a tapestry of potentialities, and the thread that weaves it into a solid fabric might be our own conscious attention. When we scale this quantum weirdness up from a single particle in a lab to the cosmos as a whole, the implications become staggering, defying all our classical intuitions about an objective external reality. The most direct and provocative interpretation is the participatory anthropic principle, famously championed by physicist John Archibald Wheeler. He took the observer effect to its ultimate conclusion, suggesting that we live in a participatory universe. In this view, the universe only came into existence because it eventually produced observers who could look back and see it. Wheeler used the analogy of a surprise 20 questions game. In this version, the person answering thinks of an object only after the questions are asked, crafting a consistent reality retroactively based on the inquiries. In a similar way, our observations of the present might be determining the history of the universe all the way back to the Big Bang. The constants of nature, the specific arrangement of particles, the very fact that the universe is comprehensible, all of this might not be a happy accident, but a consequence of the fact that we are here to observe it. Our act of measurement today could be reaching backwards through time, selecting one specific history out of a fog of quantum possibilities, forcing the universe to have always been the way we see it now. It's a concept that makes the very ground of reality feel like it's shifting beneath our feet, suggesting that the past is not fixed and immutable, but is as malleable as the future, contingent on the observations we make in the present. This radical line of thinking inevitably leads to one of the most controversial and mind-expanding interpretations of quantum mechanics, the many worlds interpretation. Proposed by Hugh Everett Roman III, this theory offers a way to avoid the special role of the observer altogether. It suggests that the wave function never actually collapses. Instead, at every moment where a quantum event has multiple possible outcomes, the entire universe splits or branches into multiple parallel realities. In one universe, Schrödinger's cat is alive and purring. In another, it is tragically dead. In one universe, the electron went through the left slit in the famous double-slit experiment. In another, it went through the right. There is no single privileged outcome and no need for a conscious observer to force a decision. Every possible outcome mandated by the quantum equations actually occurs, but we, as conscious beings embedded in one specific branch of this vast, ever-branching multiverse, only experience a single, consistent timeline. This interpretation defies our classical physics by proposing a reality of literally infinite scope, where every choice, every chance event spawns new universes. It preserves the deterministic, mathematical purity of the quantum equations, but at the immense cost of sacrificing the uniqueness of our own reality, suggesting that we are but one thread in an infinite tapestry of existence. Yet, even this dizzying concept cannot fully escape the haunting question of consciousness. If the many worlds interpretation is correct, why do we find ourselves in this particular branch of reality, one that is so finely tuned for life? This brings us back to the heart of the mystery, bridging the gap between the cold mathematics of quantum theory and the warm, subjective experience of being. Some physicists and philosophers, like Roger Penrose, have speculated that consciousness itself may be a quantum process, perhaps occurring within tiny structures inside our brain's neurons called microtubules. In this view, the collapse of the wave function isn't caused by a conscious observer in a vague, philosophical sense, but is the very mechanism that generates consciousness. It's a two-way street. The universe's quantum possibilities present a menu, and consciousness is the act of selecting one item from that menu, an act that simultaneously defines both the external world and our internal experience. This idea pushes the defiance to its absolute limit, proposing that mind and matter are not separate domains, but inextricably linked aspects of a single underlying reality. The universe isn't just observed. In a very real sense, it might be awakened by the presence of sentient beings within it, a cosmic dance where the dancer and the dance are one and the same. This mystery, perhaps more than any other, challenges not just our scientific laws, but our very place in the cosmos, leaving us to wonder if the greatest act of cosmic defiance is our own ability to look upon the stars and ask, why? But if the quantum world suggests a universe deeply intertwined with consciousness, our next mystery plunges us into a realm where the very fabric of information and reality faces its ultimate test, a puzzle born from the mind of Stephen Hawking that threatens to tear apart our understanding of physics at its seams. This is the black hole information paradox, a conflict so profound it pits Einstein's theory of general relativity directly against the core tenets of quantum mechanics. And it all starts with a seemingly simple question: what happens to the information about an object when it falls into a black hole? To understand the depth of this problem, we first need to grasp two fundamental pillars of modern physics. On one hand, we have quantum mechanics, which governs the world of the very small. One of its most sacred principles is unitarity, the idea that information is never truly lost. If you were to have a perfect, God-like understanding of the universe at this very moment, you could, in theory, use the laws of physics to rewind time and reconstruct everything about the past. The information about every particle, its type, its position, its spin is always preserved, just transformed. It's the ultimate cosmic recycling program. You could burn a book, and while the pages are gone, the information encoded in the arrangement of its atoms is still present, however scrambled, in the smoke and ashes. On the other hand, we have general relativity, which describes gravity and the cosmos on the largest scales. Its crown jewel is the black hole, a region of space where gravity is so intense that nothing, not even light, can escape its pull. According to Einstein's theory, a black hole can be described with stunning simplicity by just three properties: its mass, its electric charge, and its spin. That's it. This is often called the no-hair theorem, implying a black hole is bald, featureless, and has no other distinguishing characteristics. For decades, physicists assumed these two ideas could coexist peacefully. If you were to throw a grand piano, a collection of rare books, and a steaming cup of coffee into a black hole, general relativity seemed to say that all the intricate information about those items, the molecular structure of the coffee, the specific grain of the piano's wood, the text printed on the book pages, would be completely and irretrievably lost, crushed into the black hole's singularity, and leaving behind only a slightly heavier black hole with more mass, charge, and spin. The unique how of those objects would be erased, leaving only the boring how much. This presented a quiet tension, but it wasn't yet a full-blown crisis. The information was thought to be trapped inside the black hole, hidden forever behind its event horizon, the point of no return. It was gone from our universe, but perhaps not technically destroyed. Then, in the 1970s, Stephen Hawking made a discovery that turned this quiet tension into a roaring paradox. He realized that black holes are not entirely black. By applying quantum field theory to the curved spacetime around a black hole, Hawking showed that these gravitational monsters should slowly evaporate. The process hinges on the strange behavior of the quantum vacuum. Empty space is not truly empty. It is a seething foam of virtual particle pairs spontaneously popping into and out of existence. Normally, these pairs annihilate each other almost instantly, but Hawking realized that if such a pair appears right at the edge of the event horizon, a gravitational tidal force could tear the two particles apart. One particle falls into the black hole while the other escapes into space, stealing a tiny amount of the black hole's energy in the process. To an outside observer, this stream of escaping particles looks exactly like thermal radiation heat. This is Hawking radiation. Over immense stretches of time, this slow leakage of energy causes the black hole to lose mass, shrink, and eventually, in a final burst, vanish completely. Hawking's calculations showed that this radiation is purely thermal, like the glow from a hot piece of coal. It is random and featureless. It contains no information whatsoever about the vast collection of exotic objects that fell in over the eons. The piano, the books, the coffee, their entire informational history is seemingly erased from the universe when the black hole emits its last Hawking particle and winks out of existence. This is the heart of the paradox. Quantum mechanics insists that information cannot be destroyed. Hawking's calculations seem to show that it is. The implications sent shockwaves through theoretical physics, creating a conflict that has raged for half a century. Hawking himself initially believed that the information was truly lost, a conclusion that meant one of our two most fundamental theories of reality had to be wrong. This led to what is sometimes called the Black Hole War. On one side were those who sided with quantum mechanics and the preservation of information. Their mantra was a powerful one: if quantum unitarity fails in the extreme environment of a black hole, then it fails everywhere, and the entire logical foundation of our most successful scientific theory collapses. On the other side were those who, like Hawking at the time, were willing to consider that a new, radical principle was needed, one where information could indeed be lost, requiring a fundamental rewrite of physics. The stalemate was absolute, and the scientific community was divided over what seemed like an irreconcilable difference between our two best descriptions of the universe. The search for a resolution has generated some of the most creative and mind-bending ideas in modern physics. One of the leading contenders is the idea of holography, emerging from the work of physicists like Gerard T. Hooft and Leonard Susskind. The holographic principle suggests that all the information that falls into a black hole is not stored in its mysterious interior volume, but is somehow encoded on its two-dimensional event horizon, the surface that shrouds it. Imagine taking a complex three-dimensional object and compressing all the data about it onto a flat, two-dimensional surface, like a hologram on a credit card. When you look at the hologram from different angles, a three-dimensional image appears. In a similar way, the proposal is that the event horizon acts as a vast cosmic hard drive, storing a scrambled holographic record of everything that has ever fallen in. The information never actually crosses the horizon. It is smeared across it, preserved forever in a form we don't yet fully understand. In this view, when Hawking radiation is emitted, it is not truly random. The radiated particles are subtly entangled with this information on the horizon, and they carry it away bit by bit in an incredibly complex and encoded form. The radiation only appears thermal to a coarse-grained observation. If you could measure it with infinite precision, you would find the fingerprints of all that lost history. Another fascinating and highly controversial proposal is the black hole firewall paradox. If information is preserved and carried away by Hawking radiation, it creates a different kind of problem related to quantum entanglement. The particle that falls into the black hole and its escaped partner are initially entangled. But for the outgoing radiation to carry information, it must also become entangled with the earlier radiation. This would violate a quantum rule against monogamy of entanglement. A particle cannot be fully entangled with two different things at the same time. To resolve this, some physicists propose that the event horizon is not the smooth gateway described by general relativity, but is instead a violent wall of high-energy particles, a firewall, that instantly incinerates anything trying to cross it. This would break the entanglement between the infalling and outgoing particles, saving the information but radically violating Einstein's principle of equivalence, which states that an astronaut falling into a black hole should feel nothing special as they cross the horizon. The firewall idea is so disruptive that it is seen by many as a sign that our current theories are hitting a wall of their own, pointing toward a need for a more complete theory of quantum gravity. The most recent and promising avenue involves a deeper understanding of the geometry of spacetime itself, guided by the study of wormholes or Einstein-Rosen bridges. It turns out that the complex mathematical connections that preserve information in Hawking radiation might be geometrically represented by tiny, non-traversable wormholes that link the interior of the black hole to the radiation it emits far away. These quantum wormholes are not tunnels you could travel through, but they represent an invisible connectivity that ensures the information is never truly separated, even if it seems to be from our classical perspective. This has led to a profound realization. The old picture of a black hole as a simple object with a clear inside and outside is likely an illusion created by our classical intuition. In a quantum gravitational description, the interior of the black hole and the distant Hawking radiation might be so intricately connected that they are, in a sense, the same thing. The information was never really in the black hole in the way we thought. It was always somehow imprinted on the radiation from the very beginning, just in a form that is exponentially complex to decode. The evaporation of the black hole, then, is not a destruction of information, but its final, dramatic translation from a gravitational form into a radiative one. While Hawking eventually conceded that information is probably not lost, the precise mechanism of its salvation remains one of the most active and thrilling frontiers in all of science, a defiance that continues to push the human intellect toward a deeper and more unified vision of reality. Yet we are forced to confront an even more fundamental defiance, one that challenges our understanding of nothingness itself. This is the vacuum catastrophe, a problem so severe that it is often called the worst theoretical prediction in the entire history of physics. It is a direct collision between our two most successful theories, quantum mechanics and general relativity, and it revolves around a single, shocking number, the energy of empty space. According to the well-established principles of quantum field theory, The vacuum of space is not a true void. It is a seething, bubbling foam, a quantum arena where pairs of virtual particles and antiparticles constantly pop into and out of existence in a fleeting dance allowed by the uncertainty principle. This perpetual churn means that even in the darkest, emptiest patch of space between galaxies, there is a fundamental, irreducible energy. Every cubic centimeter of nothingness is in fact alive with this vacuum energy. The problem is that when physicists attempt to calculate how much energy this quantum frenzy should contain, the answer they get is monstrous. The calculation itself is straightforward, following the trusted rules of quantum mechanics. Theorists sum up the contributions from all the possible quantum fields that permeate the universe. The result is a density of vacuum energy so immense, so ludicrously large, that its effects on the cosmos should be nothing short of apocalyptic. This vacuum energy would manifest as a repulsive gravitational force, a form of dark energy so powerful that it would have torn the universe apart in its earliest moments. Structures like galaxies and stars could never have formed. In fact, the cosmos would have expanded at such a ferocious rate that atoms themselves would have been ripped apart before they could even coalesce. The universe would be a featureless, accelerating void, utterly inhospitable to life. The number this calculation produces is beyond comprehension. It suggests a vacuum energy density of around 120 orders of magnitude greater than the value we actually observe. That is a 1 followed by 120 zeros. To say this is the worst prediction in science is an understatement. It is an error so vast that it defies any attempt to rationalize it. Now contrast this theoretical frenzy with the serene, almost imperceptible reality we actually measure. Astronomers, through observations of distant supernova and the cosmic microwave background, have determined the actual strength of the dark energy that is causing the universe's expansion to accelerate. This observed value is the cosmological constant, a tiny, gentle pressure woven into the fabric of space-time. When we compare the quantum field theory prediction to this observed value, we find a discrepancy that is not just large but logically insurmountable. The predicted energy is 10 to the power of 120 times larger than what we see. This isn't like measuring the length of a room and being off by a few inches. It is like calculating the volume of the observable universe and getting an answer the size of a single proton. The two numbers are so incomparably different that it signals a fundamental failure in our understanding. Either our theory of the quantum vacuum is profoundly wrong, or our theory of how gravity interacts with that vacuum, general relativity, is missing a critical piece. The depth of this catastrophe becomes even clearer when we consider possible fixes. One might hope that the positive and negative energy contributions from all the different quantum fields would somehow cancel each other out, leaving a net value of 0 or a very small number. This is known as fine-tuning, and the degree of fine-tuning required here is so exquisite it borders on the absurd. For the final result to match our observations, the cancellation must be perfect to 1 part in 10 to the 120. This is a level of precision with no analog in the natural world. It would be like throwing a dart from one side of the universe and hitting a bullseye 1 millimeter wide on the other side, not just once but every single time. Such an astronomical coincidence seems deeply unsatisfying to most physicists. It suggests that some undiscovered symmetry or principle in nature must be forcing this cancellation, a principle that remains completely hidden from our current theories. This leaves us staring into an abyss of ignorance. The vacuum catastrophe is not a minor accounting error. It is a screaming alarm that our most fundamental descriptions of reality are incomplete. We have two magnificent, exquisitely tested pillars of modern physics. Quantum field theory predicts the vacuum should be raging with energy, while general relativity, armed with the observed value of dark energy, describes a cosmos expanding at a stately, accelerating pace. Both theories cannot be correct in their current forms when it comes to the energy of nothing. This defiance points directly to the need for a theory of quantum gravity, a framework that can seamlessly unite the world of the very small with the realm of the very large. Until we find such a theory, the vacuum catastrophe will stand as the ultimate monument to our cosmic confusion, a permanent reminder that even the emptiest space in the universe holds secrets capable of confounding our greatest intellectual achievements. Now, let's push our exploration into a realm where the very act of moving through the cosmos determines what you see, a theoretical prediction so startling it questions whether the particles we take for granted are even real. This is the Unruh effect, a concept that feels more like science fiction than physics, yet emerges directly from the equations of quantum field theory. Imagine you are floating in the deepest, darkest, and coldest possible region of interstellar space, a perfect vacuum where the temperature is absolute zero and not a single particle drifts by. According to all our standard measurements, you are completely alone in a true void. Now, imagine you fire up the engines of your spacecraft and begin to accelerate smoothly and constantly. As you pick up speed, something miraculous and deeply confusing happens. Your instruments begin to register a faint glow of heat. Your particle detectors start clicking, registering a bath of real, tangible particles swarming around you. To you, the accelerating observer, the freezing vacuum has transformed into a warm sauna filled with radiation. Yet, if you could instantly communicate with a friend who remained floating at a constant velocity, they would report something entirely different. They would still be sitting in the absolute cold of empty space, detecting absolutely nothing. Both of you are in the exact same location in the universe, describing the exact same patch of space-time, but your reality is fundamentally different. The very existence of particles and temperature has become a matter of perspective, a direct consequence of your state of motion. This bizarre effect is deeply connected to the Hawking radiation that evaporates black holes, and it hinges on the strange nature of the quantum vacuum. We often think of empty space as truly empty, but quantum mechanics tells us it is a vibrant, seething arena. The uncertainty principle allows for pairs of virtual particles and antiparticles to spontaneously pop into existence, borrowing energy from the vacuum for an immeasurably short instant before annihilating each other and vanishing. For an observer moving at a constant speed, this frantic activity is perfectly balanced and remains invisible. The net effect is zero, and they perceive a true vacuum. However, for an accelerating observer, this balance is broken. Their acceleration creates a horizon, a boundary in space that they can never receive signals from, much like a black hole's event horizon. This alters their perception of the quantum foam. What the inertial observer sees as a fleeting virtual particle pair, the accelerating observer can perceive as a real, detectable particle. The energy for creating this real particle comes directly from the work done by the acceleration itself. The result is that the accelerating observer finds themselves immersed in a thermal bath of particles with a temperature that is directly proportional to their acceleration. The harder you push on the engines, the hotter this ghostly radiation appears to become. This leads us directly into a philosophical minefield that strikes at the very heart of what we consider to be real. If one observer can measure particles and temperature while another, in the same place, measures nothing, then which perspective is correct? Which reality is the true one? Our intuition screams that there must be an objective, God's eye view of the universe, a single, true state of affairs that is independent of who is looking. The Unruh effect and its cousin Hawking radiation shatter this intuition. They suggest that particles are not fundamental, invariant building blocks of the universe. They are not like little marbles that exist whether you look at them or not. Instead, particles are excitations of underlying quantum fields, and whether or not an excitation is registered as a particle depends entirely on the observer's trajectory through spacetime. To borrow a famous analogy, think of a tree falling in a forest. The old philosophical question is whether it makes a sound if no one is there to hear it. The unrut effect poses a far stranger version. If one person is running through the forest and hears the tree crash while another person standing still hears nothing, did the tree really fall at all? The concept of a particle begins to look less like a fundamental entity and more like a useful tool for describing an observer's specific interaction with a quantum field. The paradoxes deepen when we consider what this means for the nature of scientific observation and the principle of relativity. Einstein's great insight was that the laws of physics should be the same for all observers in uniform motion. The unrut effect extends this, showing that even something as basic as the particle content of the universe is not absolute but is a direct consequence of an observer's motion, including accelerated motion. This creates a profound challenge for a theory of everything. If we cannot even agree on something as fundamental as whether empty space is hot or cold, full of particles or utterly empty, then how do we construct a single, objective description of reality? Some physicists interpret this to mean that we must abandon the idea of particles as the primary objects in our theories and focus solely on the underlying quantum fields, which are the true invariant entities. Others see it as evidence that our current formulations of quantum field theory, while spectacularly successful, are still incomplete, perhaps requiring a deeper theory of quantum gravity to resolve these observer-dependent contradictions. The unrut effect stands as a quiet but monumental defiance, reminding us that our most basic assumptions about the world, that there is a single, shared reality we all inhabit, may be nothing more than a comforting illusion, a local consensus that breaks down under the extreme conditions of acceleration, forcing us to question the very fabric of what we call real. But if the unrut effect makes reality a matter of perspective, then the phenomenon we explore next binds perspectives together in a way that seems to defy the very notion of separation. This is the mystery of quantum entanglement and the EPR paradox, a concept so strange that even Albert Einstein, one of the founders of quantum theory, rejected its implications, famously deriding it as spooky action at a distance. The story begins in 1935 with a brilliant thought experiment designed not to celebrate the new quantum mechanics, but to expose what Einstein and his colleagues Boris Podolsky and Nathan Rosen saw as a fatal flaw. Their paper, now known as the EPR paradox, aimed to prove that quantum mechanics was an incomplete theory. They argued that for a theory to be physically realistic, every element of physical reality must have a definite value, independent of whether it is measured or not. And for it to be complete, the theory must describe all of those elements. Their argument centered on a pair of particles that interact and then fly apart to opposite sides of the universe. Quantum mechanics states that until you measure a property like the spin or polarization of one particle, it exists in a fuzzy superposition of all possible states. The moment you measure it, its state collapses to a definite value. The spooky part is this: if the two particles are entangled, then the instant you measure particle A and force it to choose a state, particle B, no matter how far away, immediately snaps into the corresponding correlated state. According to the standard interpretation of quantum mechanics, there is no delay. The influence is instantaneous, seemingly traveling faster than light. For Einstein, this was unthinkable. It violated the bedrock principle of locality, the idea that objects can only be influenced by their immediate surroundings, and that no physical influence can propagate faster than the speed of light. He believed there must be hidden variables, unseen factors determined at the moment of entanglement that preordain the particle's fates, thus preserving a local classical reality. For decades, the EPR paradox remained a fascinating philosophical debate, a war of ideas fought on paper. The decisive blow, however, would be struck not by thought but by experiment. In the 1960s, physicist John Stuart Bell devised a mathematical theorem that could, in principle, settle the argument. Bell's theorem provided a way to test whether the correlations between entangled particles could be explained by any local hidden variable theory, as Einstein hoped, or if they truly required a spooky, non-local connection. The test involved measuring the particles in different directions and comparing the statistical correlations. If the results exceeded a certain threshold known as Bell's inequality, it would mean that no local, realistic theory could explain what was happening. The universe would have to be either non-local or unrealistic, or both. The experiments that followed, most famously by Alain Aspect and his team in the 1980s, were masterpieces of precision. They created pairs of entangled photons and sent them flying in opposite directions to detectors that could measure their polarization at randomly chosen angles. The results were clear, decisive, and revolutionary. The correlations between the entangled photons violated Bell's inequality. They were stronger than any local hidden variable theory could possibly allow. The universe had chosen spookiness. The influence between the particles was, by all appearances, instantaneous and independent of distance. Subsequent experiments have only reinforced this stunning conclusion, with entangled particles maintaining their bond across distances of hundreds of kilometers, their fates linked in a way that seems to mock the vast emptiness between them. So, what is actually happening? How can two particles communicate or appear to communicate faster than light? The truth is, we don't have a single, comfortable answer. The most straightforward interpretation is that the universe is fundamentally non-local, that the entangled particles are not two separate entities, but parts of a single, unified quantum system, no matter how far apart they are drawn. In this view, space is not the ultimate separator we imagine it to be. There is a deeper layer of reality where everything is connected, and what we perceive as a vast, empty cosmos is an illusion. The moment you measure one particle, you are not sending a signal to the other. You are simply revealing a property of the larger, connected whole. This interconnectedness challenges our most basic intuition about objects being distinct and isolated from one another. Another profound interpretation is that of superdeterminism, a concept that eliminates spooky action by making an even spookier claim about reality itself. This view suggests that the choices of what measurements to make are not truly free or random. From the moment of the Big Bang, every event, including the experimenter's decision to measure particle at a specific angle, was predetermined. The particles and the measurement settings were all part of a single, unbreakable chain of cause and effect, so there was never any need for a faster-than-light signal. The correlations were baked into the cosmic cake from the very beginning. While this resolves the paradox, it does so at the cost of free will, presenting a universe that is a colossal, predetermined machine, a notion many find as disturbing as spooky action itself. Then there is the many worlds interpretation, which offers a third, mind-bending way out. In this view, the wave function never collapses. When you measure the first entangled particle, the universe splits. In one branch, you see particle A with spin up and particle B with spin down. In another, equally real branch, you see particle A with spin down and particle B with spin up. There is no spooky action because both outcomes actually occur. From your perspective within one branch, it seems as if the distant particle instantly responded, but in reality, all possible outcomes are realized in a constantly branching multiverse. The correlation was always there, woven into the structure of reality, and your measurement simply placed you in one thread of that vast tapestry. The practical implications of this defiance are no longer just theoretical. The strange linkage of entanglement is the foundational principle behind emerging technologies like quantum computing and quantum cryptography. In quantum cryptography, any attempt to eavesdrop on a message secured by entangled photons inevitably disturbs their delicate quantum state, alerting the users to the presence of an intruder. It is a form of security guaranteed by the laws of physics themselves. Quantum computers aim to harness the parallel processing power of superpositions and entanglement to solve problems that are completely intractable for even the largest classical supercomputers. We are learning to engineer spookiness to build machines that rely on this deep, non-local connectedness to function. The enduring mystery of quantum entanglement, therefore, is not just about particles. It is a profound challenge to our understanding of existence. It forces us to ask whether the space that separates us is as fundamental as it feels, or if it is merely a stage on which a deeper, more interconnected drama plays out. This phenomenon suggests that at its heart, the universe is not a collection of isolated things, but a seamless web of relations, where what happens here is intrinsically linked to what happens there, instantly and forever. It is a defiance of locality that points toward a unity so complete and so baffling that we are only just beginning to grasp its implications for the nature of reality itself. From the deeply interconnected reality of quantum entanglement, we now turn to a theoretical device so paradoxical that it uses the very fabric of spacetime to unravel itself. This is the concept of the tachyonic antitelephone, a thought experiment that emerges from a strange corner of Einstein's special relativity. The theory itself doesn't forbid the existence of particles that always travel faster than light. Physicists call these hypothetical entities tachyons. While we have never detected one, the equations allow for them as a mathematical possibility. Now, imagine if we could harness such particles. If you could encode a message on a tachyon and send it zooming off faster than light, you wouldn't just be creating a superluminal messaging system. According to the rigid rules of special relativity, you would be constructing a time machine. The tachyonic antitelephone is the name for this hypothetical device, and its implications are far more terrifying than they are convenient, threatening to shatter the logical sequence of the universe. The mechanism behind this time-bending postage system hinges on one of relativity's most mind-bending consequences, the relativity of simultaneity. In our everyday experience, we assume that two events that happen at the same time for one person happen at the same time for everyone. Einstein showed this is not true. Whether two distant events are simultaneous depends entirely on your state of motion. For two observers moving at different speeds, there now slices through space-time at different angles. When you introduce a signal that travels faster than light, this delicate relationship breaks down catastrophically. There will be some observers for whom your message arrives at its destination before it was even sent. The mathematics is clear and inescapable. If you could send any signal faster than light, then in some perfectly valid frames of reference, the effect would precede its cause. Your reply could land on your desk before you ever decided to write the original message. This immediately launches us into the realm of classic causality paradoxes, the most famous of which is the grandfather paradox. Imagine you receive a message from your future self sent via tachyonic antitelephone. The message reads, "Do not, under any circumstances, invest in the cosmic carburetor company." Heeding this warning from your own future, you avoid the investment. But then, years later, when you go to send that warning back to your younger self, what motivation do you have? You never suffered the loss, so you have no reason to send the message. But if you don't send the message, then your younger self would have made the investment and lost everything, which would have given you the motivation to send the message after all. We are caught in an endless, logically inconsistent loop where the effect receiving the warning eliminates its own cause sending the warning. The universe is presented with a sequence of events that is fundamentally self-contradictory. It cannot find a stable, consistent timeline where all the pieces fit together. The defiance here is not of a single law, but of the very foundation of rational thought and empirical science. The entire scientific method is built on the principle of causality that causes precede effects. We form hypotheses, conduct experiments, and observe outcomes all within a forward-flowing river of time. If backwards in time communication were possible, this logical framework would crumble. You could conduct an experiment to test a theory, get a negative result, and then send a message back in time telling your past self to adjust the theory so it would yield a positive result. The experiment would both confirm and disprove the theory simultaneously, rendering the very concept of scientific truth meaningless. The laws of physics, as we understand them, seem to be structured in a profoundly clever way to prevent such logical nightmares from ever occurring. This leads to a compelling and widely held interpretation. The laws of physics as we know them don't just happen to make faster-than-light travel difficult. They inherently and absolutely forbid it to protect the consistency of causality. The cosmic speed limit of light c is not merely a suggestion. It is the universe's ultimate traffic law designed to preserve a single, coherent timeline. The prohibition isn't just on matter accelerating to the speed of light, it's on any process that could transmit information faster than light. This is why the hypothetical tachyons are so problematic. Even if they existed, any attempt to use them to send a signal would inevitably lead to a causality violation in some reference frame. Most physicists interpret this not as a quirk of math, but as powerful evidence that tachyons, if they are real at all, cannot be used for communication. They must be forever beyond our control, perhaps interacting with the universe in a way that doesn't allow for the transmission of meaningful, causal information. The profound takeaway from the tachyonic antitelephone is that the universe appears to be intelligently designed to avoid paradox. The speed of light is less a barrier and more a guardian of chronological order, a fundamental feature of spacetime that ensures cause always comes before effect for every observer in every situation. This is a defiance that never actually happens, and that is precisely the point. The laws of physics are so robust that they preemptively outlaw their own violation, building logical consistency directly into the geometry of reality. It suggests that the flow of time we experience is not an illusion, but a deeply embedded, protected feature of the cosmos, a one-way street that the universe will defend at all costs to keep the story of existence from spiraling into nonsensical, self-erasing loops. Yet even the strangest particles and the most profound quantum connections take place within a universe that, on the very largest scales, is supposed to be roughly the same everywhere. The cosmological principle, that foundational idea of a uniform cosmos, leads us to expect a kind of cosmic froth, with galaxies and clusters forming a relatively even web of matter. But when we actually map this cosmic structure, we find a breathtaking exception to this rule, a region of emptiness so vast and so profound it feels less like a void and more like a hole punched through reality itself. This is the Boötes void, a spherical chasm in space so enormous that it defies our very understanding of how the universe arranges itself. If you were to place our Milky Way galaxy at the center of this void, the nearest major wall of galaxies would be so far away that humanity likely would have never discovered the existence of other galaxies until the development of vastly superior technology. We would have gazed into the abyss for centuries, seeing nothing but an endless, empty black, our own galaxy a solitary island in a sea of nothing. The scale of this emptiness is almost impossible to visualize. The Boötes void spans a diameter of approximately 250 million light-years. To cross this void at the speed of light would take a traveler 250 million years. Within this incomprehensible volume, astronomers have found only about 60 galaxies. That may sound like a lot, but according to our standard models of large-scale structure, a region of space that size should contain well over 10,000 galaxies. The paucity of galaxies here is so extreme that the void is sometimes nicknamed the Great Nothing. Imagine a continent-sized map of the Earth where one single region, the size of the entire Pacific Ocean, contained only a few dozen small islands, while the rest of the map was packed with bustling cities and towns. That is the kind of cosmic desert we are confronting in Boötes. Its existence isn't just unusual, it is a statistical nightmare, an outlier of such magnitude that it challenges the models that predict a more or less even distribution of matter throughout the cosmos. The discovery of this void was a gradual process, a puzzle pieced together by astronomers in the 1980s. While surveying the redshifts of galaxies in the constellation of Boötes, researchers Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman noticed a startling gap. Their map of the cosmos showed a dense, nearby supercluster of galaxies, and then, beyond it, an immense empty region, followed by another distant wall of galaxies. It was as if they had stumbled upon a colossal cosmic bubble, a sphere of near-nothingness nestled between the great filamentary walls of the cosmic web. The initial reaction was one of disbelief, followed by meticulous verification. Could this just be an illusion, a shadow cast by a cloud of intervening dust within our own galaxy? The answer was a definitive no. This was a true void in the large-scale structure of the universe, a genuine vacancy on an epic scale. Its confirmation sent a ripple through cosmology, forcing a re-evaluation of just how lumpy and uneven the cosmos could truly be. So, how does such an enormous void come to be? The prevailing theory of structure formation, centered on dark matter and gravity, does allow for voids to exist. In the early universe, tiny quantum fluctuations were stretched to enormous sizes during the inflationary epoch. After the Big Bang, gravity began to work on these slight density variations. Regions that were slightly denser than average pulled in more and more matter, eventually collapsing into galaxies and clusters. Conversely, regions that were slightly less dense than average lost matter to their denser neighbors, slowly evacuating over billions of years. The universe in this picture evolves like a rising loaf of raisin bread, where the raisins the galaxies cluster together, leaving behind large bubbles of empty dough. The problem with the Boötes void is that it is far, far larger than any single raisin bubble should be. The initial underdensity required to create such a massive void through this simple gravitational process would have had to be extraordinarily large and coherent, a single, vast sinking in the primordial universe that somehow avoided being broken up by the turbulent forces of expansion and gravity. This has led to more exotic and speculative theories. One compelling idea is that the Boötes void is not a single, simple void, but the result of several smaller voids merging together over cosmic time. Imagine several soap bubbles in a sink, their walls touching and then finally popping, coalescing into one giant, unified bubble. In a similar way, smaller cosmic voids could have grown and merged, their intersecting walls of galaxies eventually dissolving, leaving behind a single, terrifyingly empty volume. Another, more radical possibility involves the dark energy that drives the universe's accelerating expansion. Perhaps in regions like the Boötes void, dark energy began its repulsive work earlier or with greater effect, actively pushing galaxies apart and preventing new ones from forming, effectively inflating the void from within. This turns the void from a passive absence into an active, expanding feature of the cosmos. The most mind-bending proposal of all is that the void is evidence of a collision with another universe in the multiverse, a cosmic bruise where the very fabric of space-time was stretched and emptied by an impact from outside our own reality. While this remains a fringe idea, it speaks to the sheer extremity of the Boötes void, an anomaly so great that it can drive scientists to consider the most profound possibilities. The enduring legacy of the Boötes void is its stark demonstration of cosmic humility. It is a permanent reminder that our models of the universe, however elegant and successful, are approximations. The cosmos is capable of producing structures and absences that lie far outside our standard predictions. The void is not empty of all physics. It is a laboratory for studying the behavior of dark energy, the evolution of the rare galaxies that do reside within it, and the limits of gravitational collapse. It forces us to ask whether it is a freak accident, a statistical fluke in an otherwise homogeneous universe, or a sign that the cosmic web is far more complex and clumpy than we ever imagined. Gazing into the great nothing is not looking into a true void. It is looking into one of the universe's most profound puzzles, a silent, expanding sphere of defiance that questions our very place in the grand architecture of everything. But the universe's defiance isn't confined to the empty spaces between galaxies. It can also be found in the most powerful objects at their very hearts, thrown into a cosmic exile. We are talking about runaway supermassive black holes, colossal gravitational anchors that have been violently ejected from the centers of their home galaxies and are now racing through the intergalactic void. The very idea seems to contradict everything we know about these cosmic monsters. We picture a supermassive black hole as the sedentary king of its galactic domain, sitting motionless at the core, its immense gravity dictating the orbits of billions of stars. To find that these titans can be kicked out, sent careening through the darkness, is like discovering that a mountain has been uprooted and is tumbling across a continent. These are not just drifting, they are flying, some with velocities of several million miles per hour, fast enough to travel from Earth to the Moon in under a minute. Their discovery forces us to confront the aftermath of the most violent dance in the cosmos, the merger of two galaxies and the black holes at their centers. The engine behind this incredible expulsion is a phenomenon predicted by Einstein's theory of general relativity, gravitational waves. When two galaxies collide, their central supermassive black holes eventually sink to the center of the new merged galaxy, forming a binary pair. They begin to orbit each other, swirling closer and closer in a tightening spiral. As they whip around at a significant fraction of the speed of light, they stir the very fabric of space-time, sending out ripples known as gravitational waves. Think of these waves not as gentle ripples on a pond, but as a directed torrent of energy like the recoil from a cannon. For the most part, these waves are emitted symmetrically, and the black holes continue their death spiral unimpeded. However, if the two black holes are of different masses, or if their spins are misaligned with their orbit, the emission of gravitational waves can become highly asymmetric. In the final, furious moments before they merge into one larger black hole, this lopsided burst of energy can act like a rocket nozzle. The newborn black hole recoils in the opposite direction, receiving a kick so powerful it can overcome the gravitational pull of the entire galaxy. It's a cosmic version of firing a bullet, where the gun is the merger event itself, and the bullet is an object weighing millions or even billions of times the mass of our Sun. The evidence for these rogue black holes is subtle, a testament to the detective work of modern astronomy. We cannot see a black hole directly, of course. Instead, astronomers hunt for the telltale signs of their recent, violent departure. One method is to look for quasars' incredibly bright beacons powered by supermassive black holes as they voraciously accrete gas that are far displaced from the dynamical center of their host galaxy. In a normal galaxy, the quasar should be right in the middle. Finding one off to the side or even on its way out of the galaxy entirely is a major red flag. More dramatic still is the search for a wake of stars. Imagine a massive ship plowing through a dense fog. It leaves a visible trail in its path. A runaway black hole, if it is still actively feeding, can do the same thing. As it barrels through the dense gas of the galactic core, it can ignite a trail of new star formation behind it, or strip a path through existing stellar populations, leaving a linear feature that points directly back to the vacant galactic center. These are the cosmic crime scene clues, the evidence of a king who has been violently dethroned and is now fleeing the scene of the crime. The existence of these runaway black holes profoundly challenges our understanding of galaxy evolution. For a long time, the co-evolution of galaxies and their central black holes was thought to be a stable, symbiotic relationship. The galaxy provides the gas for the black hole to feed on, and the black hole, through its energetic outbursts, regulates star formation and helps shape the galaxy. A galaxy without its central supermassive black hole is like a solar system without its sun. The gravitational anchor is gone. This raises fascinating and unanswered questions. What happens to a galaxy after it loses its central black hole? Does the galaxy become unstable? Does star formation run amok without the regulating feedback from the black hole's jets and radiation? Or does the galaxy simply drift, a ship without a rudder, its core becoming a ghost town? Furthermore, the ejection process itself suggests that the final stages of black hole mergers are far more chaotic and dynamic than our smoothest models predicted. The fact that these kicks happen at all tells us that the spins and masses of merging black holes are often wildly misaligned, painting a picture of galaxy mergers as violent, messy affairs, not the clean, orderly integrations we might have imagined. The implications stretch even further into the realm of cosmic demographics. If a significant number of supermassive black holes are being ejected into intergalactic space, then our current census of these objects is incomplete. We may be underestimating their true numbers because we are only counting the ones that stayed home. This also creates a population of truly isolated black holes, drifting in the immense darkness between galaxies with no gas to feed on and no stars to influence. These dark, lonely wanderers would be virtually impossible to detect, silent ghosts from ancient cosmic collisions. Their existence suggests that the intergalactic medium is not as empty as it seems, but is instead punctuated by these dark, massive exiles. The discovery of runaway supermassive black holes forces us to rewrite the final chapter of galaxy mergers, introducing a dramatic and unexpected plot twist where the most powerful character can be summarily evicted, sent on an endless journey through the void, a permanent reminder of the universe's capacity for supreme gravitational violence. Yet as we chart the gravitational echoes of runaway black holes and the vast emptiness of cosmic voids, a different kind of boundary emerges much closer to home, a frontier in our own solar system that ends with a sudden, puzzling drop into nothingness. Far beyond the orbit of Neptune, in the cold, dark outskirts of our planetary neighborhood, lies the Kuiper Belt, a vast disk of icy remnants left over from the solar system's formation. Think of it as a distant, frozen junkyard, home to dwarf planets like Pluto and thousands of smaller, icy bodies. For decades, our models of how this region formed suggested a simple, logical pattern. The number of these objects should gradually decrease the farther out you go from the sun. It should be a gentle, sloping decline, like a beach that slowly gets deeper, with icy rocks becoming sparser and sparser until they eventually blend into the even more distant Oort cloud. But that is not what we see. Instead, at a distance of about 50 astronomical units from the Sun, 1O being the distance from Earth to the Sun, the population of Kuiper Belt objects doesn't just thin out. It plummets. It's as if this cosmic beach has a sharp, vertical edge, a cliff beyond which the icy debris almost completely vanishes. This is the Kuiper Cliff, and its existence is a direct and baffling challenge to our standard story of how the solar system's outer reaches settled into place. The standard model of solar system formation, known as the NICE model, paints a compelling picture of a dynamic and violent past. It describes how the giant planets Jupiter, Saturn, Uranus, and Neptune migrated from their original orbits, their gravitational influence scattering icy planetesimals throughout the outer solar system. This process should have deposited a vast, smoothly distributed population of objects in the Kuiper Belt. According to these simulations, we should still be finding a significant number of small, icy worlds out to distances of 60, 70, or even 80O. The sudden absence of objects beyond the 50O mark is like taking a detailed geological survey of a coastline and finding that, beyond a certain point, the sand and rocks have simply been swept away, leaving a stark, unnatural border. This isn't a subtle statistical fluctuation. It's a glaring feature in the data that screams that something is missing from our equations, that some force or object has actively sculpted this distant frontier. This anomalous edge has, of course, ignited a firestorm of speculation, with the most compelling and thrilling hypothesis being the existence of an unseen, massive planet. This isn't the hypothesized Planet X of old supermarket tabloids, but a serious scientific proposal often referred to as Planet 9. The idea is that a planet, perhaps 5 to 10 times the mass of Earth, could be lurking on a highly elongated, 1,000-year orbit that takes it hundreds of O from the Sun. The gravitational influence of such a world would act like a cosmic shepherd, as it swings through the outermost solar system on its immense elliptical path. Its gravity would violently perturb the orbits of any Kuiper belt objects that venture too close. Over billions of years, this influence would have cleared out a vast swath of space, either hurling these icy bodies into the deep reaches of interstellar space or sending them plunging inward toward the Sun, leaving behind the dramatic cliff we observe today. The very emptiness beyond 50O becomes the signature of this hidden architect, a gravitational fingerprint left in the void. The search for Planet 9 is a monumental task that embodies the very spirit of scientific discovery. Astronomers are not simply pointing telescopes at random patches of sky and hoping for a lucky break. They are using the peculiar orbits of the few extreme trans-Neptunian objects that do exist as celestial breadcrumbs. A handful of small worlds like Sedna and other detached objects have been discovered with orbits that are strangely clustered, tilted, and stretched in ways that are incredibly difficult to explain through the influence of the known planets alone. Their orbital paths seem to be herded as if an unseen shepherd is guiding them. By meticulously tracking these bizarre orbits and running complex computer simulations, researchers can back-calculate the probable path of the perturbing body. They are essentially triangulating the position of a ghost, using the subtle tugs it exerts on the far-flung debris of the solar system to pinpoint its possible location in the sky. It's a cosmic game of pool where we are trying to deduce the position and mass of the cue ball by observing how all the other balls have scattered. However, the Planet 9 hypothesis, while elegant, is not the only possible explanation for the Kuiper Cliff. Some scientists propose that the cliff might be a primordial relic, a fossilized edge from the solar system's birth. Perhaps the protoplanetary disk of gas and dust from which our system formed simply ended more abruptly than we thought, its material truncated by a close stellar flyby from a sibling star in the Sun's birth cluster billions of years ago. In this scenario, the disk was sheared off, leaving a natural, sharp boundary that was imprinted before the planets even finished forming. Another, more radical idea involves the gravitational influence of the galactic tide itself. As our solar system orbits the center of the Milky Way, it bobs up and down through the galactic plane. The collective gravity of all the stars, gas, and dark matter in the galaxy exerts a subtle but persistent tidal force on the outer solar system, much like the Moon's gravity pulls on Earth's oceans. It's possible that over the eons, this galactic tide has stripped away the most distant Kuiper belt objects, slowly eroding the population beyond a certain critical distance and creating the observed cliff. Yet, while these are valid alternatives, they often struggle to explain the full suite of orbital anomalies as neatly as the single, massive perturber of Planet 9. The enduring mystery of the Kuiper Cliff, therefore, is more than a debate about a missing planet. It represents a fundamental gap in our understanding of our own cosmic backyard. We have sent probes to every known planet, landed rovers on Mars, and even touched the Sun. Yet the outer dark of our own solar system still holds profound secrets. The cliff is a stark reminder that our planetary system does not have a simple, well-defined edge, but a complex and dynamically active frontier that is still being shaped by forces we have yet to fully comprehend. Whether the culprit is Planet 9, a galactic tide, or a primordial scar, Its discovery has already reshaped our view of the solar system, revealing it to be a far larger, stranger, and more dynamic place than we ever imagined, with its final borders still waiting to be drawn. After contemplating voids, black hole ejections, and the edges of our own solar system, we arrive at a puzzle woven into the very first light of the cosmos, a problem so fundamental it challenges the core narrative of the Big Bang itself. This is the horizon problem, and to understand it, we must envision the universe as we see it in its infancy. The cosmic microwave background, that pristine snapshot from when the universe was a mere 380,000 years old, shows a remarkable and frankly baffling feature. Its temperature is almost perfectly uniform. From every direction we look, the temperature of this primordial radiation is the same to an astonishing degree of precision, about 2.725 degrees above absolute zero, with fluctuations of only about 1 part in 100,000. At first glance, this seems like a sign of a calm, well-mixed beginning, but a closer look reveals a profound contradiction, a cosmic traffic jam that should never have happened. The problem lies in the speed limit of the universe, the speed of light. In the standard Big Bang model, without any additions, there simply hasn't been enough time since the beginning for heat or information to travel from one side of the observable universe to the other to equalize the temperature. Imagine two people standing at opposite horizons of the Earth, so far apart they are completely beyond each other's sight and hearing. Now, imagine they are both holding cups of coffee at the exact same temperature, down to 1,000th of a degree. You would assume they had somehow communicated or shared their coffee to achieve this perfect match. In the early universe, regions of space that now appear on opposite sides of our sky were like those two people, separated by a distance so vast that light, the universe's fastest messenger, could not have traveled between them in the time available since the Big Bang. They were outside each other's particle horizons, meaning they were never in causal contact. They were cosmic strangers that had never exchanged a single photon. According to the basic rules of physics, there is no possible way for these disconnected regions to have negotiated a common temperature. The universe, in its first moments, should be a patchwork of hot and cold spots that never had a chance to even out. The fact that it isn't suggests that the rules we thought were absolute have been defied. It appears that information about temperature traveled faster than light, or that some other mechanism forced a uniformity that standard physics cannot explain. This paradox demanded a radical solution, and in the early 1980s, a brilliant and elegant theory emerged: cosmic inflation. The proposal was as simple as it was revolutionary. What if, in the very first fraction of a second after the Big Bang, the universe underwent a period of breathtaking, exponential expansion? Not the steady, stately expansion we see today, but a violent, hyper-fast stretching of space-time itself. The numbers involved are almost incomprehensible. In a time span as short as 10 to the power of negative 32 seconds, a decimal point followed by 31 zeros and then a 1, a subatomic speck of space is thought to have inflated to a size larger than our entire observable universe. This wasn't an expansion into space, it was the rapid creation of space itself, and it happened at a rate far exceeding the speed of light. While nothing can move through space faster than light, there is no such restriction on the expansion of space itself. Inflation used this loophole in the laws of physics to solve the horizon problem in one dramatic swoop. Here's how it works. Before inflation, the entire observable universe was crammed into a tiny subatomic volume. This microscopic region was so small that every part of it was in direct, intimate thermal contact. It had plenty of time to reach a uniform temperature, to smooth itself out into a perfectly mixed state, just like a cup of coffee that has been stirred thoroughly. Then inflation kicked in. This unimaginably rapid stretching did not create new heat or matter. It simply took that tiny, already homogenized patch and blew it up to a cosmic scale. The entire sky we see today, from one horizon to the other, was once a single, causally connected neighborhood that was stretched apart to become the vast cosmos. The perfect uniformity of the cosmic microwave background is therefore not a mystery. It is a fossil, a relic of that brief period when everything was close enough to talk, before the great inflationary expansion pulled it all apart. The regions that now seem disconnected were once next-door neighbors, and their matching temperatures are simply a memory of their shared, compact origin. While inflation beautifully resolves the horizon problem, it does so by introducing one of the most profound and elusive mysteries in all of cosmology: what caused it. The mechanism behind this ultra-rapid expansion remains one of the greatest unsolved puzzles in physics. The leading theoretical candidate is a hypothetical energy field called the inflaton field. Think of this field as a kind of cosmic fuel that permeated all of space. In the earliest moments, this field was in a high-energy state, a false vacuum, and its immense pressure generated a powerful repulsive gravity. This repulsive force, not dark energy, is what drove the exponential expansion of inflation. As the inflaton field decayed and relaxed to its true, lowest energy state, it released its pent-up energy, reheating the universe and filling it with the hot plasma of particles and radiation that would eventually form atoms, stars, and galaxies. The inflation we observe today is essentially the afterglow of this colossal release of energy. Yet, for all its theoretical elegance, the inflaton field itself remains entirely speculative. We have no direct evidence for its existence, and the precise details of how it started, why it lasted as long as it did, and what made it stop are active and contentious areas of research. Inflation's legacy is a double-edged sword. On one hand, it is a towering achievement of theoretical cosmology, successfully explaining not only the horizon problem, but also the origin of the tiny density fluctuations that seeded all cosmic structure and the remarkably flat geometry of the universe. It has become the standard addendum to the Big Bang Theory, a crucial chapter in the story of our origins. On the other hand, its very success raises deep philosophical questions. If inflation can happen once, what is to stop it from happening again in different patches of space-time, creating an eternal, self-replicating multiverse of bubble universes, each with potentially different physical laws? This idea pushes the boundaries of testable science, as these other universes would be forever beyond our observational reach. Furthermore, while specific models of inflation make predictions that have been confirmed, such as the precise statistical pattern of the CMB fluctuations, the theory as a whole is so flexible that it can be adjusted to explain almost any observation, making it difficult to falsify. The horizon problem, therefore, has led us to a stunning resolution that simultaneously answers our most pressing questions and opens the door to mysteries far grander and more perplexing than we ever imagined, leaving us to wonder if we have solved a cosmic puzzle or simply discovered a deeper, more complex layer of reality hidden within the first moment of time. And so we reach the end of our journey through 30 breathtaking instances where the cosmos has stared into the camera of our scientific laws and winked. From the phantom tug of the Pioneer anomaly to the galactic superhighways carved by runaway black holes, from the chilling silence of the Wow signal to the seething, paradoxical vacuum of empty space itself, we have traversed a landscape of profound and humbling mysteries. Each one of these cosmic riddles, from the grandest scales of dark energy to the most intimate quirks of quantum entanglement, serves as a stark and magnificent reminder that the universe operates on a logic far more complex and wondrous than our current textbooks can contain. They are not merely errors in our data or gaps in our knowledge. They are the universe's way of teaching us, of pushing the human intellect beyond its comfort zone and into the uncharted territories of what might be possible. This incredible voyage reveals a beautiful and essential truth about the scientific endeavor, that our greatest progress is not born from certainty, but from curiosity in the face of the unknown. These 30 cosmic defiances are not failures. They are the very engines of discovery. The anomalous orbit of Mercury in the 19th century was not a flaw in Newton's gravity, but a signpost pointing toward the curved spacetime of Einstein's general relativity. The perplexing stability of atoms once threatened classical physics, only to birth the revolutionary world of quantum mechanics. In the very same way, the Hubble tension, the black hole information paradox, and the vacuum catastrophe are not dead ends. They are blazing beacons illuminating the path to the next great theoretical leap, a theory of quantum gravity that will, we hope, weave together the very large and the very small into a single, coherent tapestry of understanding. They force us to build better telescopes, design more sensitive detectors, and dream more audacious dreams. The quest to solve these puzzles is what propels our technology and expands our imagination, driving us to become a more knowledgeable and insightful species. So as you look up at the night sky, remember that the tranquil, twinkling vista is a grand illusion. Behind that veil of cosmic calm lies a reality of staggering violence, profound emptiness, and logic-defying phenomena that challenge our most fundamental notions of existence. The universe is not a passive backdrop. It is an active, dynamic, and often rebellious participant in our quest for knowledge. It invites us to keep questioning, to keep exploring, and to never lose our sense of wonder at the sheer, magnificent strangeness of it all. The greatest adventure is not in finding all the answers, but in embracing the journey of asking better and more profound questions. We want to hear from you on this ongoing journey of discovery. In the comments below, tell us which of these 30 space-defying laws you find the most utterly mind-boggling. Was it the phantom push of the M drive, the cosmic conspiracy of the axis of evil, or the lonely exile of a runaway black hole? Share your thoughts, and let's continue this conversation about the most incredible mysteries of the